Hey, hello. Welcome on the second day of the XDC conference, streamed live from Gdańsk. Thanks, Richard, for your great work yesterday. We all hope, I guess, that this experience and flawless execution will be continued today and the day after that. I hope that everyone enjoys the event so far, and I don't plan to take too much time today going through the logistics. Before that, let's just give a round of applause to all our sponsors. Without them, this event would not be possible. So, big thank you goes to our platinum sponsor, Intel, second time in a row. Our gold sponsors, Google, NVIDIA, ARM, Microsoft, AMD. Thanks a lot for sponsoring the XDC. Our silver sponsors, Igalia, the Linux Foundation, Collabora. Thank you for your support. Thanks for support to our bronze sponsors, GitLab and Kronos Group. We would also like to thank you to our supporter this year, C3 VOC, for providing us great streaming service. I hope everyone enjoys it. Organizers this year, big thank you to organizers, to our organizing team, which I proudly represent, to Intel and X.Org Foundation. Thanks for bringing this experience to all of us. Some useful information. As yesterday, the live stream URLs and all the data that you may be needing to attend the conference and participate actively in the talks, asking questions, is on our website. Please follow us on Twitter, where we are posting the latest updates and answer some of the questions that you may have. Any questions to the organizing team, reach out on IRC, on OFTC. Most probably everyone by now is aware of who to contact, but just reminding in case. Streaming this year is available on both YouTube and Media CCC.de. Links, as mentioned, are on our website, so please go and check it out. We have hallway discussions possibility this year as last year. If there is any need, you would like to discuss some topics that were tackled or mentioned yesterday in any of the talks, maybe you have some other ideas you would like to discuss with other attendees, make sure you use the instance and post the link to the room you've created to the XDC 2021 channel on IRC so others are able to join. And don't forget to think about creating lightning talk at the end of the conference on Friday, so everyone can know what you've been discussing, and maybe there will be some fruitful ideas coming after that. The program is available on our website. A reminder to everyone, it's in UTC+2 time zone, the organizer time zone. So if you would like to see it in more familiar hours, go to my preferences, use my time zone, and set it to yes after logging into Indico. Lightning talks and are still allowed for Friday afternoon. First come, first served. So make sure that you let organizing team know ahead that you will be presenting something. We would love to see lightning talks covering all hallway discussions and also whatever is after the workshops that are starting soon. About workshops, this is the first day where we will have workshops on XDC this year, starting really in parallel with the first talk this year, in the main track. So Martin Perez will be working with other people, attendees, to talk about coordinating the CI efforts. Probably more information will be shared just after I finish this opening session. If you would like to add workshop, there is still a chance. Contact me on IRC and we'll work it out. Thanks to all the speakers that already uploaded their presentations. We have just a couple of gaps. So make sure that your slides are available to all the attendees and also to people that would like to review the material after the conference, or in their preferred time zone, and see which talks they'd like to listen to first. So this is great help for us organizers and also to attendees. So make sure you find some time and upload your slides. In X.Org Foundation and our organizing team, we are all dedicated to providing harassment-free conference experience to everyone. We do not tolerate harassment, and this is very important for us that all the breaches that happen are raised with us. And if you spot some behavior that you think should not be happening, make sure you either send email or contact us via IRC. More details and the whole code of conduct is available on our webpage. Make sure you check it out. That's all for today from me. I hope you'll have great another day of the conference. Thanks a lot again to all our sponsors, and have a great second day of XDC. Thank you. See you around.
Once again, welcome to XDC 2021. It is day 2, and up today are 8 talks and 2 workshops. Speaking of which, the first of those is coming right after the break, coordinating the CI efforts for Linux in user space, led by Martin Perez. Here are a few words from the organizer. As you saw yesterday, CI farms are starting to appear for more drivers than just Intel. There are, however, a lot of remaining challenges, especially related to trace execution and bringing kernel testing to GitLab. Join us if you want to make your desktops and Steam Decks write upstream without regressions. If you are interested in only one topic, we'll start with the trace-based testing for an hour, then finish with kernel-based testing later. In parallel to the workshop, there are 3 talks, starting with David Edmondson's addressing Wayland robustness. We hope you have a great time. See you in a few minutes. And we're ready to go with the first talk of the day, which is David Edmondson's Addressing Wayland Robustness. David, please take it away.
Hello, and welcome to my talk, Addressing Wayland Robustness. My name's David Edmondson. I've been a KDE developer for over 10 years, and I'm one of the maintainers of Plasma, our desktop environment, which means I'm trying to make sure our Wayland transition goes well, not just from the point of view of a compositor, but as the entire desktop. But I'm not here representing KDE. I'm a contractor for Valve, and they're trying to look at ways to make this user experience better across all your desktops, make Linux in general better. So the most important question I need to answer is, what do I mean by robustness? It's a key word in the title. And by robustness, I mean the ability to handle an error. When we're writing code, we always add in checks. We always ask the question, what if this fails? Even though something shouldn't fail, things inevitably will. And it's important to try and handle errors in a useful way. So the alternative title of this talk is, My Compositor Crashed. You won't believe what happened next. Obviously, you will believe it because there's a video at the end. So what's the current state on Wayland? How robust are we? Well, if we take example of Western, you've got it open, a crash happens, which we can simulate by typing kill-9 Western. And I have a bunch of open documents. I've got LibreOffice, or I've got this thesis I've been working on, or some in the middle of moving some files in a volatile way. What happens if Western crashes? Well, all of those programs exit. And even if they don't exit, we're taken back to Login Manager, and systemd comes in and starts killing all of these processes. And from the user experience, anything that involves data loss is known in the industry as bad. So we want to avoid that. So can we do better? Well, it would be a fairly short talk if the answer was no. So yes, we can. And I want to introduce a method I've been working on called compositor handoffs, which is a very fancy title for a very simple concept. It's a mechanism for clients to resend their current state to a new compositor. Because a client is a canonical source of what windows it has, or what windows it thinks it should be showing, or what content is in those windows. So it can just send them again. And arguably, this is even more robust than on X11. On X11, your compositor could crash, but if the X server went down, you would still lose all your data. So what we're here able to do now, because a compositor and a display server are now one thing, if we move this problem into a client, we get to address both those problems at once. And this wasn't possible on X11. On X11, there were too many blocking calls, there were too many server-side allocations, too much point-to-point communication. And all of that goes away in Wayland. So even though it seems like we've taken one step back, it's actually an opportunity to take 2 steps forward. So what are the key benefits? What is the reason for doing this? So I briefly talked about the obvious one, crash handling. I'm not going into a bit more detail. I mean, realistically, all software crashes. I know I've set myself up for a cheap joke about Quinn, but pragmatically, we can open the automatic bug reporting tools for any of the major distros and see crash reports upon crash reports for all of the different compositors. And that's just the very nature of software. In particular, I think we have a problem with compositors because they're taking on more and more responsibilities. So video streaming, you're responsible for proxying all of the input. There's more and more things in that single point of failure. And we do want that for your security. It does have a lot of benefits. Things can be faster. But it comes with a cost that we need to start protecting against. And the other problem is the Wayland world is still changing. I remember a day when the X11 server would crash relatively often enough that they literally had a shortcut to handle freezes. And that was on by default because it happened enough times to warrant it. And it got to a point that we stopped changing X11, and then that was able to stabilize, and I think that was a killer part. But the Wayland world is still changing. There are new protocols every day. By the time I finish this talk, there'll be another protocol up on Wayland protocols for us to implement. As we still try and find all of these niche edge cases that haven't been figured out yet, and the world's still changing because we now have the opportunity to start doing interesting tech at the compositor level again. But it's not just about crashes. The developer experience. We always want to dog food our own code. We want to be running our own code constantly. And the problem is, I don't want to log out and log back in again every time I want to test some changes or every time I recompile the latest master. And what was happening on Wayland for a long time is I simply wouldn't. My personal compositor doesn't crash very often because if it did, I would have fixed it. So I can end up running a compositor that's 2 months old on my laptop where I've just been closing a lid, and then I'm missing out on actually testing what's going to be released to our users. So we remove this barrier to testing. If I can just easily type Quinn Wayland replace as easily as I could back on an old X11 compositor, it makes that testing cycle a lot faster, a lot easier. But there are more benefits. An interesting idea that we get to explore in the future is the idea of switching compositors. So I could start a client talking to a waypipe being sent remotely, and then at a flick of a switch, transfer it over to Quinn. Or vice versa, if I start something on one machine and then go to another. And that would allow for the fastest way of doing remote transfers. We could get to do true multi-head. Currently, you can do a multi-head situation where you start a client on one compositor, and I know you could have a different compositor managing another physical screen, but you can't move clients between them. And there are use cases for that. It might be niche, it might be a very odd case, but we would be able to open up some interesting possibilities. Another thing this opens up is checkpoint restore in user space, or CREU. And checkpoint restore in user space is a system where we can take an application that's running and save it to disk, and then at a later point in time, potentially after a reboot, or potentially 2 weeks later, restore it out of disk into your RAM and just continue the process running as it was. And if you read the documentation for checkpoint restore in user space, it's a big paragraph about why this can't work in X and why it can never work in X. And all of those reasons apply to what we currently have in Wayland. If you start sending IDs over a proxy a compositor isn't aware of because the compositor's been restarted, it will obviously just hit an error and get closed. So we need a way for a client, after it's been restored, to just resend all of its current state to the compositor and start with that clean slate, which is what we've been working on. So what's needed for clients to be able to reconnect? The first step we needed to solve was a race-free way of doing compositor restarting, because if a compositor goes down and a client comes down at the same time, the client could come up before a compositor, at which point it would try to connect to a socket that doesn't exist and bail out again. And we didn't want to just put it in a loop or something. So we needed to come up with something a bit better, and this is the one change that's on the compositor. So we make a Wayland socket on disk persistent, and we do this by having two processes: a very tiny helper process that creates a Wayland socket and then passes a file descriptor to your compositor. Very much like system deactivation, and that would absolutely work as a solution. We just ended up rolling our own version for a few technical reasons. So if the compositor crashes, the socket remains. And if a client tries to come up early before your compositor is restarted, it will block when it's trying to read and write and connect to that socket. This is race-free. It also helps us improve our startup speed, so it's something that I would recommend everybody do anyway. Like I was reading a code for GreetD the other day, and they have to set up these complicated daisy chains of starting this process, which starts Sway, which then starts to Greeter, and it's so much, you get a much cleaner system if you can have a single process, set up your socket, and then just tell everyone to go at once. So everything's secure because helper process is still the starting query. Nobody else can come along and pretend to be a compositor. And the client, very importantly, can distinguish a compositor crashing and being able to reconnect from a compositor closing. Because if a compositor just closed, the helper would close as well, and then there's nothing to connect to. And we really want to have that signal available to clients. What do we need to do on the client side? Obviously, the most important part of all of this. Well, in theory, it's quite easy. We need to handle the screens disconnecting and reconnecting. From the point of view of a client, the W outputs have gone and we have some new WR output objects. But screens can change dynamically at runtime anyway, so we need to have code in our toolkit for that already. We need to pretend every device on our WLC has gone and then we have a new WLC full of devices. And again, this is something that the toolkit needs to be prepared for anyway. The toolkit's bound to have some code to handle a state. We need to recreate our window contents, the buffers, but we need to recreate our Windows buffer every time you do a resize or draw a new frame. So the toolkit's bound to have code for this already as well. And we need to reset the Windows shell, make that new XG top level and everything that goes along with it. And this part is technically new, but certainly within Qt we actually had to have code for this anyway because it was possible through our public API to switch between being a main window and a tooltip after you've shown this window, which isn't possible in Wayland, so we needed to have that code to tear that window down and recreate it. So the point is, a lot of the time we're just trying to hook into all of the existing points that already exist. There isn't a lot of new code. Everything that has to happen when we connect to a new compositor is just calling code that we have to do anyway at other points. It's just a case of mashing it all together. So I've got some example code. Somewhere in your toolkit, in your application, you'll be checking for an error. You'll be checking to see what our error code was and then exiting. All we need to do is when we notice that we've got a connection error, we reconnect the display, we delete everything, we create a new registry, set that up, and then once we call the round trip, we'll reinitialize all of our globals. And then we need to reiterate through all of our windows and reshow the contents. Obviously, this is slightly simplified, but ultimately not too much. So now, putting this into practice, I've been going around several of the main toolkits and clients trying to prove, is this something that's actually viable? Does this work in the real world without needing to change a bunch of applications? Can we just make some very small toolkit changes? Needed somewhere to start, so I want everyone to think about the most important Linux application, the one you almost certainly use on a daily basis. I know this is pre-recorded, but I also know everyone's thinking exactly the same thing. Super TuxCart, very important client, but realistically it was also a simplified, good demo. So this is an SDL. So one of the first things I did was I patched SDL. I didn't touch any code in Super TuxCart, that's important to mention. I only patched SDL. And to have full reset support for recreating all your windows, recreating all your buffers, and mouse cursors and such, was only 173 lines. This is less code than it takes to support middle click paste. So it's definitely viable from that point of view. It goes harder than middle click paste, but it's a very small manageable amount. And obviously, being a KDE developer, I patched the Qt clients. So I patched Qt. This is quite a bit more work in SDL. It's a much more involved, it's a bigger toolkit. We have threaded rendering to worry about. If you're using Qt Quick, one of our new graphical toolkits, you've got your main thread handling most of Wayland connections, but all your rendering's happening elsewhere, and we're doing a WL surface commit from that thread using a queue being done by Mesa. We have drag and drop, data devices, all of these additional protocols. We have multiple shells to worry about. It's not just XG top level. We also have IVI and some custom shells. layer shell. And it's a much larger API in general. But when I made those changes, every application just works. And in KDE, we have literally hundreds of applications written in Qt. And I didn't have to touch any of those applications, and they just worked. I've yet to have a problem with anything that we classify in KDE as an application. There is one slight caveat on that. There are some shell components, like a clipboard manager, which is using some custom Wayland code. That's not going to work out the box. But anything that's just using a toolkit and using abstraction layers has just worked. And that goes from large text editors, from kdevelop, video editors. No other changes. And one of the other big players, which is a different case, is X.Wayland. And I packed X.Wayland, and I wanted to see if I can pack X.Wayland, pretty much anything else is doable. And the X.Wayland changes were relatively straightforward. There was a very nice, helpful function to just recreate everything for a given X11 window, and it would recreate all the surfaces and buffers and pointer locks and everything else that we needed. All the buffer code was fine. The challenge in this is because our lifespan of the X.Wayland and compositor is different, we do need to redo the startup sequence. We can't rely on the compositor creating a file descriptor for X.Wayland to connect to, because we want that X.Wayland connection to outlive the compositor if it needs to. We also need a compositor to outlive X.Wayland if X.Wayland goes down, which is something we also have code for. So it becomes a bit of a chicken and egg situation of trying to handle new ways of handling the initial synchronization. But we were able to come up with something that works. That's not deployed yet, but we're able to make all of X.Wayland work. And one nice thing about X.Wayland is because the positions are being held by a client, if the compositor does go down, all your windows are still in the same place. Firefox. Obviously, Firefox is massive, and if you're a compositor developer, you know Firefox does some interesting things, like having multiple data devices and things that we know are special cases. It's going to be a big thing to do, so I didn't patch Firefox. But the reason I mention it is because we did something slightly interesting, is you're able to, because Firefox has its own very, very, very good crash handling already, we can make use of that. It could be wrapped in a small script, probably better than this one, to handle your case. And it means if a compositor does go down and we restore and we reconnect, sure, you get a small prompt saying, this has happened, do you wish to restart all your windows? Maybe we could optimize that in some way. But it works. And the reason I mention this is because if the strategy puts everything in the responsibility of the client, we don't need to have a one-size-fits-all strategy. It might be best for your client to do something different. We want to get the toolkit support where possible in Qt, SDL, GTK, X.Wayland, but maybe there are special cases. Moving on from this is shell components, where we have the panels and our clipboard managers. Maybe it doesn't make sense to try and make them survive a restart. Maybe it's just easier to have them restart. And that's what we currently do in Plasma. We just restart a Plasma shell with the panels because there's not a lot of persistent data in the panels. We don't need to try and solve that slightly more complicated case if doing a simpler option just works. So we have a bit of flexibility. So I'll give a demo of all of this working. Start a demo. I've got SuperTuxCart open because obviously this works for any SDL client. I just picking this one because it features Conky. And if we fake a compositor crashing, and we can see everything restored exactly as it was. Still got input, still got my GL context, still got my amazing rain effects, still losing erase. But it doesn't just work for SDL. I mean, we can saw my console survived. We can open system settings, or Kate and leave some unchanged changes. So you could make a point. And again, restart Quinn. I've got my unsaved changes, my important documents here, my settings. Even though this is all Qt powered with subsurfaces, just works as expected. But what about under the hood? What changes did we need to make at a very lowest level that's going to be shared across all the different toolkits? Probably the biggest challenge in all of this porting work is OpenGL, because every application needs to draw a 3D port somewhere. And we're finding lots of applications use this. It's a very critical part. It's also a standalone independent library. It's not quite at a toolkit level. So most applications will have a single EGL display object, and it's shared throughout the client code. It might be created in the toolkit, but you'll be passing it around as a native pointer for clients to do their low-level drawing code. And most importantly, it takes a WDisplay object in its constructor to be able to commit buffers and create the DMA buffers and the like. So we need a meta code to react to when we get this reset, to clear up the WLDRM objects, the DMA managers, and all of the globals. But at the same time, we want that same EGL display object to persist in the client space. This means we need some Wayland changes. So we know if the EGL display object has to persist and takes it in a constructor, the WLDisplay object has to persist. So we added a new method, WLDisplay reconnect, which does exactly what you would imagine. It reconnects. And WLDisplay gets a new notification. We've got a method with a reconnect listener where you pass in a callback, just like other Wayland callbacks. Whenever WLDisplay reconnect gets called, the notification gets fired. Mesa can now listen for a signal and react accordingly. And all of this work has been done. The toolkits don't need to do anything. This is one part that's now very easy to do in all the toolkits. OpenGL just works. And from a client point of view, it's very convenient. Your client's connection to your rendered device is completely untouched when we reset your compositor. So all GL context objects remain intact. Any textures you've uploaded, any vertex buffers, are all completely untouched, even though we're now connecting to a new compositor. The only thing we need to reset are WL surfaces and therefore any EGL windows and EGL surfaces. But clients should be going through and resetting this anyway. So the clients only need to worry about a small part of resetting, and then they can use all of their drawing code exactly as before. Another change we added to Wayland was this concept of lazy reinitialization. When we call that WLDisplay reconnect method, all proxies that we know about that haven't been cleaned up yet are marked as defunct. If you're in a defunct state, the destructor can still be called. You can still call the destructor on any of these proxies, and it will do a relevant deletion. But critically, nothing on these proxies will ever be sent on over a wire, because obviously the ID is one that the compositor doesn't know about, and it will get out of sync. And this allows for a couple of useful parts. We can do thread safe reinitialization. The main thread can reconnect, but the render thread can think it's still reconnecting and sending methods, and it will just start no-opping at the right time. But that saves having to draw all of the threads to a stop while we perform this reconnect. We also have a situation of unreachable proxies. Quite often, particularly in X-Wayland code, there would be some native display type at a toolkit level where we abstract a concept like a cursor, and hidden inside the blob would be some proxies which we were unable to access from within our WLDisplay reconnect handling when we needed to handle a reconnection. So by having this flag set, we were able to deal with this at the right time when it's convenient. Whenever we then need to do something with that proxy, then we can do reinitialization as needed. It also allows for a lot easier porting, because hypothetically, if I'm porting a new toolkit and I forget to reset WL data device, instead of it crashing straight away, what I will now see is a lot of errors appearing on the screen whenever we try and use this defunct proxy. But it won't immediately crash, it won't send garbage to your compositor. And that makes life a lot easier to see what's actually happening. So, assuming you use Wayland directly in your application, what do you actually need to do? It's the exact same case as Mesa. We have that signal, you can listen to it, you can perform any relevant cleanup. And this is something that we have to do in KDE. We have some of our library code will do some Wayland additional extras, such as monitoring idle time, or we have a path to add a completely unnecessary stupid blur effect to Windows. And all of that has to react to these changes. So it allows other bits of library code to react if needed. But what's the worst case scenario? What if I've got some code where we haven't made these changes, where we've got these defunct proxies and things aren't working? I mean, most of the time, without defunct handling, it will just no op. So you might just lose a feature, but nothing terrible will happen. But if it is critical, things will just crash. But the good part is, that's no worse than what happens now. Right now, if the compositor goes down, the client crashes. So we have quite a low baseline to beat. Without bragging as my skills as a programmer, it's hard to get worse than everything breaking and dying. So things can only get better. So what's the current state of all of this work that we've done? Well, it's amazing. I've been using the Qt resetting since around January, so it's been 8 months. And it's been held off while we try and work on these other toolkits and try and prove this is a system that can work globally. But I've had it on my local machine for quite a long time. And as I said before, it really, really helps that developer experience. I can type Quinn Wayland replace, and I have a new compositor without losing my console where I'm currently working, where it's in the right directory and has everything I want. And what's the next steps that we need to do? Obviously, all of this needs upstreaming. I sent an email to Wayland Devel a couple of weeks ago. There was some feedback from Enlightenment where they're actually doing a very, very similar mechanism. We need to add GTK support, which I'm trying to do now. We need to add wine support. As they're getting a Wayland stuff ready, it should be a very convenient time to do it. I've mentioned OpenGL, I didn't touch the Vulkan side. It should be a one-to-one mapping. And maybe we want to improve some of the shared abstractions. In every case, as always, cursors prove to be a difficult part of reporting, just because of the way the SHM port abstracts a little bit, but not enough to make this convenient. So maybe there's some opportunity to share a bit more code. libWayland API is quite raw, so one-to-one with the protocol, but having a few helpers for registries and things might make things easier for everybody. And how can you run this code today? There's quite a lot of projects that had to be touched, so this wiki page is a link of all of the projects I've mentioned so far. I'm sure everyone will have lots of questions, so I've added a lot of time available for them.
Okay, thank you very much for the talk, and now we'll start the Q&A session.
Thank you.
Notifile asks, I'm kind of curious how GL works with Creo.
There's actually a talk about that yesterday, where some people are trying to make that happen and work. So that's really worth checking out for underhood stuff. The other option we have available is, especially for NVIDIA, we have this concept of a context loss event where you lose everything and have to reset all of your OpenGL state. So if anything, my Wayland work is very similar to that OpenGL work of something's gone down, it's up to you as a client to reset everything. So it is a mechanism that we could hook into.
Emergent asks, any plans to fix the race when stopping a compositor and restarting with a new one?
So if you're using the same compositor, we have fixed this race. So Quinn, for the last 2 releases, has been released with this race fixed. We've got our 2 helper process system where helper app persists. And I think what we want to do with making a change like this is to do it in small baby steps. So your first step will be making it so that you can have one compositor restart and you get that same compositor back, because that also simplifies a lot of client expectations. And then moving on to this idea of being able to switch from one compositor to another, that's a slightly more adventurous change that we're putting in the foundations for, but then might still have some more work to do on that later. So I haven't tried to solve that second problem, but we have everything solved for what we want to do initially.
And one more question from me. Would it be possible to use this mechanism in combination with something like Creo to essentially emulate a mechanism similar to Apple's handoff?
And it sounds like an interesting idea. Do you want to tell me what Apple's handoff is?
Basically, you can take an application with some state on one device and continue that application using that application on another device with more or less the same state.
I think this doesn't solve it, but it unlocks a problem. Because right now it's not possible at all for a number of reasons, but one of which is a client would immediately try and talk to your compositor and start telling it about IDs that your compositor doesn't know about, and then immediately get killed. So we solved that one problem, because from the point of view of a client, it just has a sudden amount of changes all coming at once. It gets told your buffers got swapped or it didn't get swapped, and it gets told the screens have suddenly changed and the input device all changed. But then we're just hooking into code that already exists. So there's a lot of surprises for your client, but all things that should be able to deal with.
Okay, looks like that's all the questions we have for today. Thank you very much for your great talk, and have a great rest of the conference.
Thank you very much.
Okay. And now we're ready to go with the next talk of the day, which is Tony Zwaserka, Compiling Vulkan Shaders in the Browser, A Tale of Control Flow Graphs and Assembly. Tony, please take it away.
Hi. When working in low-level software such as graphics drivers, writing the code is only part of the job. The other part comes in once you ship to production and the bug reports start flooding in. So at that point, as a developer, you have to sit down and figure out, why are games crashing all of a sudden? Why is there a rendering glitch in my game? And why is there a performance regression all of a sudden? Figuring out the source of these problems can be quite non-trivial sometimes, because what you're looking at is not the graphics driver in isolation, but instead the application running on top of your actual project. So sometimes you sit down for a day or two and you find a problem immediately, and other times you just stare at the screen for weeks after weeks, not understanding what's even going on, until that one day you finally find the problem. It's a one-line fix, just swapping one magical constant for another, and the problem is magically gone. Whenever something like that happens to me, I do celebrate my victory eventually for a bit, but then I sit down and ask myself, what could I have done differently to make this more painful? In particular, what kind of debugging tools would I have liked to have at my disposal to make my job easier here, so I can waste less time debugging this? Today we'll take a look at one tool I wrote to make understanding the structure of shaders used by retail games more quickly. So naturally we'll see a lot of shader code, we see some fancy graphs, and also we might see the first Vulkan driver running in the browser. My name is Tony Zwaserka. I work as a contractor with Valve on improving the state of Linux graphics, and welcome to my talk. Now, what do I mean with debugging tools, though? On the CPU side, there are actually a couple of categories I'd like to distinguish here. The first one begins when you actually compile your program already. It's the compiler itself. The compiler tells you about missing return values and functions, about unused variables, about potential integer overflows and something like that. And it's a really valuable resource for finding bugs early. And there's tools such as Clunktidy that perform even more advanced static analysis in your program. The more traditional category is, of course, GDB itself, but also tools such as perf and strace. And there's tools that allow you to inspect the low-level view of your program, such as object dump, and the reverse engineering tools IDA and Ghidra. There is dynamic instrumentation, such as Valgrind and ASAN, which allow you to detect bugs in your program at runtime, such as integer overflows. And then there's standard interfaces such as /proc and dbus that allow you to extend your own programs with interfaces that help people or external applications access information specific to your application. Now, when looking at this list, I was asking myself, okay, this all works on the CPU side. What if I'm working on a GPU program? What if I'm working on a game? What if I'm working on my graphics driver? We don't really have any good tools to inspect things that happen on the GPU. One example. I've written a very simple application that just renders a triangle using a simple fragment shader. The fragment shader colors everything below a certain line in a grayish tone, that's this 0.4 branch, and everything above the line in a whitish tone. To do so, it just compares the fragment coordinate in the program against the hard-coded constant. If you run this program using RADV debug shaders, then the graphics driver RADV will output its intermediate representation for the AQIR for the shader to standard output. And if you're anything like me and you've never seen this before, you will stare at this and be completely lost probably. The first time I looked at this, I was just completely overwhelmed. So the first thing I did was to bring a little bit of structure into this and reorder the blocks in a graphical representation, something like this. And I think that already helps a lot because you can quite easily see the binary structure. Although the edge connectivity between the blocks is somewhat misleading, perhaps. We see why that is in a bit. Now, I don't really have time for every single shader to get my pen and paper, and write such a graphic each time. So I was asking myself, is there a way to automate this process? And well, I wouldn't be giving this talk if the answer were no. So yes, indeed there is. I've written such a tool. I call it Shader DNA, and this is what it looks like. So in the beginning, there's a blank canvas, and what you can do is there's a text field on the left where you can just enter any kind of AQIR. There are other ways of input, but we'll get to that in a moment. But once you input the shader like that, the tool will automatically create a graphical representation of the control flow graph of this program. And that is super useful, isn't it? Because now, just by looking at this graphic and without understanding the details of the AQIR, you can immediately see, okay, there's two branches in our program, one using the constant 0.4 and the other one using the constant 0.9. Now, whenever I'm showing these graphics, feel free to ignore any of the details like this phi node here or the parallel copy instruction. We really just care for the general structure of the programs for the purpose of this talk, because that's what the tool mainly focuses about. And as you're seeing, the whole tool runs in the browser, actually. The presentation itself runs in the browser and the tool is embedded in it. At the end of the presentation, I'll be sharing a link, though, where you can try it out in your own browser. And yeah, I've kind of just quickly hacked together this prototype in a few days and then just went going from there. So after a few days of having this graph render, I started just building on top of that and seeing where my journey leads us. And now, after a couple of months, it's gotten quite advanced, I'd say. So the first thing that you notice actually here is that this is already a simplified view. Instead of showing all the connectivity information that's contained on the left, it only really represents the programmer's view of the program. The programmer's view is just a simple branch, so it makes sense that there's an entry block, an exit block, and then the two branch bodies. But actually, Shader DNA can show you a different view of the same program, which is the hardware view. The hardware view looks a little bit different, because now instead of having this the split in the control flow, the edge connectivity is just from one block to the next, to the next, to the next, to the next. So our blocks now are being executed in strict sequence. And if you're anything familiar at all with how GPUs work internally, that will immediately make sense to you. It's because GPUs are so massively parallelized that they always run programs in units of 32 or 64 threads. So branching doesn't really combine well with that paradigm. So GPUs kind of emulate branching with this concept called execution mask, which is one we see here. So whenever we execute this body that assigns 0.4 to the pixel value, instead of doing branching, the GPU will just disable all of the threads for which that assignment should not take place. And then in this block, it inverts the execution mask, enabling all of the other threads of the current unit, and then it assigns 0.9 for those threads. Now, all of that sounds very technical, but ultimately, the structure, again, is just what matters here, so don't worry about it too much. The cool part is, though, that Shader DNA allows you to switch between those two representations on the fly. Now, if you look at the full interface at the top, you see this linear setting and the logical one. This allows you to just freely swap between the two. And you see, if you care about the low-level details, particularly useful for optimizations, you can take a look. But if you only care about what is the shader doing, the logical view is ideal for that. And if you fancy, you can enable both at the same time even. But let's stick to the linear view for a moment, because I was actually kind of cheating before. The actual program does actually look like this. I was abbreviating it a little bit before. Now, what's going on here? Well, it turns out if the current group of 32 pixels that is being processed in a single unit is all above a certain line, let's say all in this whitish area, then what's even the point of executing these instructions? So ACO, the shader compiler used by RADV, actually emits a kind of shortcut branching where all of the threads just skip this block entirely and jump straight to the assignment of the 0.9 value. This is particularly important for bigger blocks, but we still emit it for simple programs because why not? But you can see with all of that optimization and fanciness, the linear CFG is just blowing up quite a bit. So again, even for the complicated program, the logical view gives you a simplified idea of what's happening in the program. There's also a disassembly view. So if you paste in disassembly code, it can also render the control flow graph for that. So here the graph looks a little bit different, but if we post both of them in the same text area, you actually get a somewhat similar structure. So it can use the information from the ACOIR to order the blocks accordingly, but it will still render the disassembly. But you can sort of just switch freely between the two if you want to. Now let's take a look at a somewhat more complicated example. And you can see this doesn't even fit on a single slide anymore. We can't fit it on a screen. It doesn't really help. Let's take a look at the logical control flow graph though. Well, that makes a lot more sense, doesn't it? We can now see that there's a block with a circular path leading back to itself. And what does that mean? Well, it's a loop. And if we look at the loop body, there's a very suspicious looking add with a 1.0 to a fixed variable that is used at the top here for a comparison. So that suggests this variable is a sort of loop counter, and the whole thing probably is a for loop, meaning that this is the path once the condition of the for loop terminates, leading to the program end. And indeed, if you look at the source code of the shader that was used to generate this one, it's indeed just this for loop comparing against the fragment coordinate and adding 0.005 to the output color in each iteration. So what this generates is just a gradient on the triangle, making much more sense. Now, you might ask yourself, okay, why was the linear view so complicated there? Well, again, this is because of the hardware model and how AMD GPUs process threads. You always have to process groups of 32 or 64 threads at once, meaning if half of your threads are already done with the for loop, they still can't exit it because the other 32 threads are still carried around. So you only need to disable those first 32 threads while still running through the through the for loop for the other ones. And I find that particularly funny, actually, because if you look at the logical CFG, once we reach this block, we're done. But in the linear view, there's actually a path pulling us back into the loop precisely because of this issue. So I think this model is quite useful to, like, for beginners as well, just to learn about what the difference between these two intuitive model and the hardware model of execution are. But again, just for developers as well, it's really useful to bring quick understanding into how a game's shaders work. Speaking of though, how about real shaders? Because we've only looked at these toy examples, and it would be really annoying if for every single game you're debugging, you would have to copy-paste thousands of shader lines of code from the terminal into a web browser. So one tool that makes this actually quite easy to work with is Fossilize. Fossilize is kind of the Steam shader cache, for those not familiar. Fossilize is a tool that allows you to capture the shaders used by an application and then play them back at a later point, similar to RenderDoc, just that it only really captures the shaders and compiles them. So it doesn't capture any assets, no textures, no 3D meshes, and it doesn't render anything. Why is that useful? Well, precisely if you want to optimize your shader compiler, you have a database of the shaders used by a game, and you can just quickly access them and recompile them without having to launch the game over and over again. There's a tool called Fossilize Replay, which you can call on such shader caches, which we also call fossilized databases, by the way. Once you call Fossilize Replay on such a database, it will output some debug information about the application, and then it will start processing shaders. So once you enable RUDB-debug again, you will see in a standard output the disassembly of all the shaders compiled during Fossilize Replay execution. If you want to play around with this, you can try this at home actually if you have Steam installed, because all the Steam games just create fossilized databases by default in this path down here. Right. So the idea that I had was, with the shader control flow visualization of shader DNA, combined with Fossilize would make for a great combination, because instead of having to enter all of your shaders manually, you could now just drag and drop a file into the browser and it would just pass all the shaders for you. So that's what I did. At the bottom here is a link to one of the Sasha Willems examples from the Vulkan examples repository. If I just download this, I can drag and drop this into the browser. You can do this with any file in your local hard disk. Just go to your file explorer and drag and drop it into the browser. And a lot of things happen, but the first thing you probably noticed is it immediately loaded the first shader of the shader database. And again, it's a fairly complicated shader. You can try to fit it on the screen. It's really somewhat big. But again, we have the logical control flow graph view, which cleans it up a little. And with that, we can see quite easily, despite not being able to read any of the instructions, we can immediately see it has this cascade of nested if-else-if statements. Just going into else, 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 whenever an if hits, it just skips right past it. But the more interesting bit about this is actually the top line here. Because this is not just a single shader, but all of the shaders used by that Vulkan example. So you can swap between the graphics pipelines, so the shaders basically, freely. In this case, there's only 4 of them. You can change between vertex and fragment shader and the other ones. And you can even change between the AQIR and the disassembly of the shader. Which, yeah, again, it's quite something, but as you might imagine, it's quite handy to just have this central tool where you can easily compare the AQIR, the higher level of representation, and the final assembly code of the shader. Now, if you've seen this, I should have probably stressed that these fossilized databases, they only contain uncompiled shaders. So they contain the SPIR-V code. How does it get from the SPIR-V code to the AQIR, though? It's not contained in the fossilized database, so apparently shader DNA must be bundling a shader compiler. And the browser? How does that work? Huh. Well, if only there were an open source shader compiler we could easily integrate into the browser, but there is no such thing. But we've got Mesa. So let's port Mesa to WebAssembly. Now, there is actually a toolchain that allows us to compile native libraries written in C and C++ to JavaScript or WebAssembly. It's called mscripton, and it works just like any other cross-compiler. So we can actually integrate this quite cleanly into Mesa's build system, which is Meson-based. And we just need to write a cross file to tell Meson about how the compiler toolchain is structured. So we tell a little bit about the binaries. EMCC and EM++ are just the equivalents to GCC and G++, as you might expect. We tell a little bit about the compilation target. And finally, we specify some like some compiler options specific to mscripton, such as generate WebAssembly rather than JavaScript, build as a web worker so we can run things in the background, and some more things that are not really all that relevant for this one. If you want to try that out, you can do so using Meson build. Just pass it in as a cross file, and it will pick up all the right binaries, and then build it using Ninja. Now, it wasn't quite that easy to get it working. It didn't just magically compile like that. One major obstacle was actually that RADV itself does not currently build without LLVM, despite having its own shader compiler these days. So I had to refer back to Emmanuel's work about allowing RADV to build without LLVM. And I tidied it up a little and added some polish so that nowadays we can actually build RADV without LLVM. An alternative would have been to build LLVM, the compiler framework itself, with mscripton and create an LLVM build that's executable in the browser. I actually did that and got it working, but the annoying bit is that it blows up the runtime size dramatically, and you do not want to download a 25 megabyte JavaScript file just for launching the tool. And also it made compiling the shader significantly slower. So I really wanted to avoid that if possible. There's also a stash of a couple of minor patches, really not all that bad. I was surprised how pleasant the porting process actually was. Indeed, most of the things I did was just removing things like runtime configuration with XML config, or adding dummy implementations of some module that is not really used, disabling debug functionality that we're not really using on the browser. None of that really was specific to, like, there wasn't any specific if mscripton else hacks. It was more about disabling functionality than anything else. If you want to take a look at these, this code, it's all public. And my GitLab branch right here. So feel free to take a look and give feedback if you have anything to add. But yeah, it's all there. Now about rendering those fancy graphs, how does that work? Well, I'm actually using a tool called Graphis, and it's amazing. It's genuinely fantastic. If you ever need to create reasonably polished graphs with very, very simple code, very little code even, Graphis is the tool of choice. So how does that work? You basically write your graph definitions in a DSL just by specifying a list of nodes. And the nodes are, in our case, the basic blocks defined here. A list of edges, just with this magic arrow. And then you define some ordering relations just to tidy things up a little. So here, the first two nodes are put on the same vertical position, for instance, and the program exit block is put at the very bottom. And there's some extra attributes to add styling and whatnot, but yeah. If you want to generate a graph from this, you just take this, save it in a source.dot file, and then run it through Graphis' .renderer tool with the right parameters. And if you do that, you get something like this. So it's not the most pretty graph, but I think it's a reasonably nice looking out of the box look, really. And you might imagine with custom fonts and some extra formatting, you get a really polished look out of this already. Again, Graphis is a native tool though, so we need a JavaScript build of that. Luckily, this has been done before. This repository provides an mscripton build for Graphis, and it's super easy to use. You just define your .source code in a JavaScript variable and then call this layout function. What this will do is it will return a string of the SVG source code of the rendered image. You could also render a PNG file, but SVG has one major benefit. It looks the same, but you can embed it in a web page. And by embedding it in a web page, you can actually interact with it. And that's not only useful to allow the user to select and copy paste text out of it, but it also enables you to add interactivity to your program. If you noticed before, when you hover over the variables in shader DNA, then you actually highlight all of the uses of that variable, which is only possible because the graph is rendered as an SVG. Otherwise, it wouldn't be easy to add that kind of feature. Right. So that's basically the two major building blocks that I wanted to show. Just a quick overview of how it all ties together. And yeah, at the beginning, of course, we have the shader database as a fossilized database, which might come from a Steam cache or just from a manual capture. We run that through libfossilize, which is basically fossilize replay, but ported to JavaScript again using mscripten with some custom additions. And this is just a regular Vulkan application. So it goes through all of the libvulkan loader, then into the radv entry points, then into the ACO shader compiler. And finally, the front end extracts the compiled shaders using the vk get shader info AMD extension. Now, all of those 4 steps are part of the mscripten-powered WebAssembly build of Mesa, which is kind of amazing, right? We're not taking any kind of shortcuts here. We're actually compiling the full stack of Mesa with this cross-compiler, and it just magically works, which definitely is a testament to how stable and robust mscripten has become nowadays, because you just take this super complicated piece of software and it just works, just works in the browser. Now, with the compiled shader, we hand that over to ShaderDNA's shader block parser, which takes a look at the disassembly of the shader and clusters the instructions into the basic blocks and tries to find the connectivity information between them so that it finally can construct the control flow graph and emit that as a dot file, which we then run through the graph-based renderer, where it will produce an SVG file, which is then integrated and displayed on the front end. Right. Now that's just one way of inputting. The other thing we've seen at the very beginning is there's a text input field as well, where you can just paste your shaders directly. In this case, you just bypass all of Mesa and you jump straight to the shader block parser itself, where it will just analyze the shader directly. But funnily enough, I actually added a separate separate path here, where you do feed the text input, if it's ACOIR, right back into Mesa. And for that, I actually wrote an ACOIR parser that will reconstruct the data structures used by ACO for that particular shader to allow it to bypass radv and libvulkan themselves and turn the shader from ACOIR into disassembly directly. Funnily enough, this is actually kind of the first offline compiler build of ACO that we have. Currently, it's tightly coupled to radv itself and cannot be used without. But with ShaderDNA, you can indeed paste an ACOIR shader into the browser and use ACO independently like that. Now, if we come back to the previous example of the fossilized database, this might make a little bit more sense now. So if I'm taking the fossilized database and dragging it into the browser again, you can see it has now used libfossilize to parse all of the shaders in that database, and it's now accessible through this combo box. You can easily browse between them, and whenever you select a new shader in here, that is where the Vulkan loader is invoked, and radv and ACO are compiling the selected shader. And this is also why you can freely switch between ACOIR and the disassembly, because again, it's just running the shader compiler in the browser. Now, if you've been listening so far, you're probably in either of two camps. The first camp is probably, oh my god, how cool is that, and when can I use this already? The other camp is more like, okay, it looks kind of cool, but why would you go through all of that trouble? Why would you do that? Instead of just maybe you could have written an imgui tool that does the same thing, but without having to port Mesa to mscripten. And there's actually a couple of reasons why I prefer to have this tool run in the browser itself. And the first one is probably most striking even. It's that we get all of the things that are available in the browser as a platform for free. So we get all of the default widgets, we get easy styling using CSS. You get accessibility features because other tools such as imgui, I think, don't really provide that all that easily, whereas in the browser it's reasonably standard and quite easy to figure out how to do that. And also you get access to all of the tooling that's available in the browser, from the performance monitor over to the DOM inspector. Everything is just there, and you can use that to sort of debug the debugger. The other thing that I haven't really talked about at all yet is TypeScript. The front end of shader.dna is written in TypeScript, and it's, compared to C and C++, really convenient for this kind of interactive user program to have a garbage collector, to have concurrency primitives, and to have a regex engine that actually works. This is just things that the language gives us for free, and it makes development of these user interactive features so much more convenient. One other thing is there's a rich package ecosystem, which shader.dna doesn't actually use that actively. I think it only has 1 dependency so far, 2 if you count Graphis, 3 if you count Mesa in. So I could go nuts and use all sorts of different packages, but really all I'm using right now is a base64 encoder for one particular collaboration feature. But it's still good to have that base64 encoder just ready to use rather than having to write my own. Finally, WebAssembly is kind of a key technology in all of this, because as you've seen, all of this runs in the browser, so you get virtually no compilation delays when switching between shaders. You just select them, and within a couple of milliseconds, the compiled shader is there. If we hadn't had WebAssembly or, well, mScripten in general available, then we would have probably needed to come up with some sort of server with some sort of back-end front-end architecture here, which means we would have needed to set up a server backend involving a server infrastructure in particular. And all of that gets really nasty. And in particular, you also need to worry about the communication between the backend and the front end. And overall, you would never get the same user experience, because just talking to a server takes time. And that's what this kind of delay is what I wanted to avoid in this tool. Now, with all that being said, you might be asking yourself, what's in store for the future? And I have a couple of plans, actually. The first one being, I want to have broader GPU support here. You might have gotten the impression that shader.dna is completely specific to AMD. And indeed, that's true for now, but there's no inherent reason for that. It's just the one driver that I happen to be using at home. So that's been the main development focus for now. But you could just as easily port any of the other Mesa drivers to the tool. And it should be doable with reasonable effort. I'm not sure I want to do the work myself, but if you're interested in picking that up, I'd be more than happy to support any kind of efforts in that direction. Similarly, I don't just want to expose AMD and AMD disassembly and ACOIR, but I want to enable shader.dna to display all of the different representations throughout the lifetime of a shader. So starting from SPIR-V, possibly even GLSL, it should be possible to display the nearcode, the ACOIR, and the disassembly, all of them at once. I actually even have a prototype for that available, at least for near and SPIR-V. GLSL is a different beast, but we'll get there. And finally, I want to have more introspection features, which I think could be particularly useful for game developers who need to have an understanding of how well their shader will actually perform on native hardware without having to get that hardware necessarily themselves. So ideally, you could just enter any kind of shader and browse through different sets of GPUs and show, okay, how does this shader perform on NVIDIA hardware? How does it perform on AMD hardware? How does it perform on Intel hardware? That's kind of the long-term goal here. And with that, we're coming to the end. So here's a couple of resources. First of all, of course, the link to the shader.dna instance itself. You can just open that in your browser and drag and drop any of your Steam shader caches into that and play around with it. If you don't have Steam, you can also use the public repository shaderdb here, which bundles some of the Sascha-Willems Vulkan examples, which can also just be used easily. Other than that, I have another special gem for you, actually. If you happen to be familiar with the Dolphin, GameCube, and Wii emulator, you might know they have this special code path called Uber shaders, where they emulate basically large parts of the full GPU in a single vertex and fragment shader. So I couldn't help myself, and I just created a fossilized capture of that Uber shader and tried loading it in shader DNA. And the link that I'll be posting will show you how that looks like. And with that, thanks for tuning in, and I'll be handing it over to future me and their host for the QA.
Okay, and that was a talk by Tony Vasorka, who is with us for the QA talk. So, Jason Ekstrand asks, can you use this tool to visualize near or other backend IRs? If not, do you have any plans to add support?
So currently it cannot do that, but I have a local patch for that, which is work in progress. So in the future, the idea is to have not only disassembly and ACOIR support, but also the higher level representations like near, like SPIR-V, and perhaps in the future even GLSL. As far as other backends goes, that's something that's not currently supported, which I would need support from the respective driver developers if they're interested. So if, say, you wanted to have Intel support, some things would need to be done, such as making sure that the Intel driver compiles with mscripton, which might require if-defing out some DRM bits, for instance. And the shader block parser itself would probably need some adjustments for the disassembly format used by Intel. But yeah, other than that, I'm certainly interested in support for other backend syntaxes as well. Yeah.
Okay, and Vinimo asks, would it be possible to add a graph visualization of the instructions in a block too?
It would be possible. I'm not sure how that would look like. If you can create any kind of mockups for that, I could consider it, yeah.
And Jason Extract asks one more thing, RenderDoc integration?
What's that RenderDoc integration?
Don't know. Okay.
But RenderDoc integration, it's, yeah. I suppose you would have to bundle a web engine for that in RenderDoc. So that's probably not something that's worth considering. But the general approach probably could be ported in some way. I'm not sure. I haven't considered it.
Okay, and looks like that's all for questions today. Thank you very much for the great talk, and have a great day.
There was one thing I wanted to add, actually. A small correction. For one thing I said in the very beginning is that I said that GPUs just all use execution masks for control flow. I did want to correct that. That's, of course, not true. It's specific to AMD GPUs. And we've seen in Alyssa's talk yesterday that other GPUs tend to work quite differently. That's just something I wanted to add. Other than that, thanks for having me.
Thank you very much as well. Have a great conference. Okay. And we're ready to go with the next talk of the day, dissecting and fixing Vulkan rendering issues in drivers with RenderDoc by Danilo Piliev from Igalia. Danilo, please take it away.
Hi, in this talk I am going to show you how to use open source debug tooling, RenderDoc in particular, to find the origin of non-trivial issues in the real-world games and applications. It is something that all of us have to do, but the methods aren't well documented and everyone has some tricks up in their sleeve. So I think this talk would be especially useful for someone who is starting to debug various games. But I like to think that even seasoned veterans would find a couple of useful tricks. But before, briefly about me. I started on the other side of the barricades. I've been a game developer and witnessed the horrors of the mobile drivers, when they were in a much worse shape than now. Afterwards, I accidentally was offered to work on Mesa, and debugged all kinds of issues in various games and applications since then. Since late 2020, I am at Igalia, now working on open source Vulkan driver for Adreno GPUs, called Turnip. As a graphics driver developer, one faces many different bugs. A lot of debugging is making educated guesses, however there are always generic things to try first. Here you could see a few examples of the issues I investigated in the past. The bottom one is the flickering of geometry in The Witcher 3 on Intel's GPU, which was the most insidious issue I debugged. It was random, it was impossible to inspect up close, hard to narrow down, and at the end it required a workaround which worked for unknown reason. Fortunately, a lot of issues are much simpler than that, and mostly have a generic flow for investigation, up to a certain point of course. For the purpose of choosing how to debug the issue, I categorize them by two distinct characteristics. The biggest concern for us is temporal stability of the issue. The issue which happens across several frames and in the fixed place is easy to capture and relatively easy to debug. On the other hand, if the issue happens randomly, and what's worse in a single frame, it could be impossible to capture and much harder to debug. Orthogonal to stability is how the issue manifests. If colors are incorrect, the first thing you would look at are textures and fragment shaders. If it is geometry that is wrong, one would look at vertex shader and incoming vertices. For hanks, you would look everywhere, unless you got some useful information from the kernel. The cause for the issues could also be categorized. Undefined behavior of an application is usually found with validation layers, or by inspecting a single frame, or cause across several frames. Shader miscompilation is also likely to be found by inspecting the frame. On the other hand, missed or wrong updates of the GPU state could be harder to find, and hardware bugs are all over the place. Later I'll talk about different tips to how to debug different issues. But now, let's take a look at the real-world issue I fixed in Turnip earlier this year. It happened in a Droid game called Genshin Impact. The game had a major misrendering in the main menu, which you could see in this slide. The game shouldn't be that blue. The steps I'll take are easily generalizable to a big chunk of issues. I followed them myself more times than I could remember. This issue was stable across frames, was not a regression, and seemed to be some kind of a shader issue. So the easiest way was to analyze the frame. For this, our only open source option is RenderDoc. I left aside the troubles of capturing this frame. So here, it is already opened in RenderDoc. The first thing we should check is whether the misrendering is captured by RenderDoc. Sometimes, especially when an issue is caused by the lack of synchronization, we will see perfectly correct result in the capture. It could be a good clue. In our case, yes, the misrendering is present in the final image, and it looks the same as in the game. Now we will try to find a draw call which caused the misrendering. RenderDoc could show which call or call range changed the erasers. In our case, we are likely interested only in FBO rights, so we should follow them. Alternatively, you could do some kind of bisection by selecting calls in the event browser you could see on the left. So let's follow the FBO rights. When you try to find the first incorrect call, keep in mind that the issue may happen in a range of calls instead of some specific one. So if they are receiving a slightest double and triple check your findings. Otherwise a lot of time could be wasted in the steps which would follow. We seem to found a render path with the issue. Now we should find the draw call. And double check that is the right one. Here is our call. It looks like some kind of a post-process effect. Now that we have the call, let's check that the issue is not in the shader inputs. There are 3 ways to do it. Eyeball the inputs, compare the inputs to a driver where the frame is known to be correct, or run the shader with the same inputs on a different hardware. The last method is easy with RenderDoc. It has a software SPIR-V and the XDC shader interpreter we can use. However, keep in mind that it does not handle everything and may refuse to work. In example last time, it didn't work with float controls extension. To debug fragment shader, I am selecting a pixel and pressing debug. This would bring us to the shader debugger. Since we are interested in the color, we should note the output variable for the color. Then skip to the end of the shader and compare resulting value with the one from GPU. They are different. But wait a minute, here we see the color that shader produced. But the color in our FBO is blended. So we are comparing apples to oranges. Fortunately, we could just clear the FBO to a white color just before the draw happens. That's better. Correcting for the blend, the values are still different. So most likely it's a shader miscompilation. But for completeness sake, let's eyeball the inputs. The only texture is a depth buffer. It's hard to see anything, but there is a button to narrow down the color range in such cases. The buffer seems fine. The spot where you check the inputs and say, it is fine, is based mostly on experience and intuition, but if there are doubts, it's better to capture and inspect a similar frame on other GPU, where it is rendered correctly. This takes time and not always possible, so it's faster to use intuition until you hit a dead end. Next ones are UBOs and SSBOs. Usually it is hard to tell if they are fine. I mostly assume that they are, unless I see nuns or other strange values. Then there is mesh and variance. If we had troubles with geometry, this would be the first place we should have checked. Since geometry doesn't trouble us, the only thing to check are the variants. Again, without a direct comparison, it is hard to tell whether they are fine. Sometimes they are just obviously wrong. We reviewed the inputs, and we are back to the fragment shader. Firstly, we should check NIR and GPU assemblies, which could be done with the help of VK pipeline executable properties extension. Unless you have NIR or assembly interpreter in the head, and I think some of you may have one, you could just look for weird constructions, some rare or unexpected instructions, or possible warnings. Here we have NIR translated from SPIR-V, NIR after all optimizations, and native GPU assembly after all optimizations. I see nothing fancy here, which leaves us with bisection of the shader. RenderDoc helpfully allows us to decompile the shader into GLSL and edit it. In most cases, the compiled shader compiles back without any trouble, but sometimes it requires minor changes to function names. Firstly, it is good to check if compiling the decompiled shader back changes anything. It could happen, and would indicate that we likely aren't handling some SPIR-V construction, which just goes away after a compilation. As you could see, nothing changed. Then we should proceed with shader bisection as promised. The idea is simple. We go into the middle of the shader and output some variable which took many previous instructions to calculate. Compile the shader and compare the output with RenderDoc's interpreter. Now repeat until we find the issue. Since we are selecting a variable based on intuition, we may miss the interesting one. In such case, we would just backtrack and be a bit more careful. Usually, I dump variable near the flow control, write to external memory, or rarely used function. I wrote the first chosen variable, and its values seem to be 1, given the blending. Now, let's see which value RenderDoc will compute. For this variable, the values are the same. Let's pick another one further down the shader. Let's see what we have in this one. I already see some strange values. They shouldn't be that big. Will RenderDoc give the same values? No, they are completely different. Then we should check the values assigned to this variable. This one has a small value. And this one too. But after assignment, in the if statement, we see a completely different value. We should recheck it to be sure. Yes, they are completely different. Then likely this is if statement, which causes miscompilation. We should look into result in assembly. We are left with roughly this snippet from the shader, which is incorrectly compiled. Since it is an if statement which causes the issue, we will have to pay special attention to the corresponding instructions in the GPU assembly. I obtained the assembly with pipeline executable properties extension. This is the beta assembly from the code with the if statement. This is the good assembly where we removed the if statement. What could we do with them? Going line by line, both assemblies should produce expected for them results. The only suspicious instruction is selection instruction, which corresponds to the if condition in the original code. We were getting unclaimed values. They were above 1. It is not something that could be produced by saturation, which clamps the value between 0 and 1. So maybe saturation modifier doesn't work. The easiest way would be to directly edit the shader's assembly. Unfortunately, we cannot edit the assembly through RenderDoc. There is no Vulkan extension for this. Maybe we could make one? There were many times I could have used it. What else could we do? Some drivers, including Turnip, have the ability to replace a shader assembly given the shader hash, which we could use to test our theory. After editing the assembly, I concluded that removal of the saturation modifier doesn't change anything. However, if I move the saturation modifier from the selection instruction to the instructions which produce its sources, the issue disappeared. Together, this means the saturation modifier doesn't work on a selection instruction. I double-checked it in a standalone reproducer, and search the assembly from the proprietary driver to see whether it ever emits such construction. It did not. After confirming it, it was trivially fixed by preventing saturation modifier from being applied to this instruction. This concludes my example, and as I said, the steps I followed are applicable to many issues you may face. What are the other useful RenderDoc capabilities? The most useful for us are, firstly, being able to view and export any input to the pipeline. Vertices, UBOs, SSBOs, textures, everything you may want. Possibility to inspect the state of any shader stage, to inspect variance between each shader stage. This variance inspection is possible thanks to the most cursed Vulkan extension, VKX Transform Feedback. Next one, Software Debugger for SPIR-V, is a relatively recent addition, and as we have seen, it is very effective, allowing to find the issue without resorting to making and opening the capture on another GPU. However, there are possible improvements to be made for our use case. In example, evaluate all fragments and show the difference with GPU result. Or being able to immediately view the result after shader edit, without closing the tab, pressing debug, going to the end of the shader, and so on. Another one is even more recent addition is the support for printfs in the shader. In Fragment Shader it is easy to just output the value to the FBO, bearing the blending of course. However, for other stages, printf is truly welcomed. I also want to highlight the Python API. With it you could add new UI widgets or automate tasks. Maybe we could make some plugins to ease the debugging. The only task I actually automated in the past was the searching for the first call which produces different outputs, giving the same inputs between several runs. Sometimes you find that misrendering is caused by the wrong inputs to a shader, and these inputs are always different between runs. This could be hard to narrow down, especially when a game uses a lot of compute shaders juggling many intermediary buffers. I automated it, which helped me a couple of times. Another useful feature is the pixel history. It allows to quickly find which draw call writes the fragment to the FBO. When there are hundreds or thousands of draw calls, it could be rather useful. And the final one are draw call overlays. Highlighting draw call and making a mesh wireframe makes easy to identify what exactly current draw call has drawn. The stencil test visualizes which fragment passed the test or was rejected. Displaying infinities and not the numbers could show us potential issues in a shader. The usefulness of clearing before the draw I already demonstrated. As mentioned previously, there are also certain limitations. Synchronization issues tend to go away in the capture. However, not every issue that is not reproduced in the capture is a synchronization issue, and vice versa. It is impossible to inspect interframe issues, which is a big limitation, and there is no other open source tool to fill the gap, since GFX Reconstruct doesn't have the ability to inspect anything. Capturing a hand could be tricky or plainly impossible. Sometimes hand completely hangs a device, or even if not, it may destabilize application enough for RenderDoc to fail. You cannot edit shader inputs or any Vulkan call parameters. This is another big limitation. The ability to edit parameters was quite helpful in API-Trace when I debugged issues with OpenGL. RenderDoc requires a lot of RAM for capture, which may not be there on ARM devices. The last one haunts Turnip at the moment. I could replay the trace of a game, but couldn't make a capture to investigate the misrendering. Which brings us to the issue that captures are not compatible between different GPU vendors, sometimes between GPU generations, and even driver versions. It poses an issue in the cases where we cannot make a capture on the target device due to a hang or because application doesn't run on the device, or target device doesn't have enough of memory. It could probably be solved by memory remapping like it was done in GFX Reconstruct, in conjunction with device simulation Vulkan layers. Sometimes you cannot make a right capture because the issue appears only for a few frames, or there is a hang causing capture failure. First one could be worked around by making a trace with GFX Reconstruct, replaying it frame by frame to find the one you want, and telling RenderDoc which frame to capture from GFX reconstruct trace. Helped me a lot in the past. If there is a hand causing failure of a capture, you could try to make the hand go away by any means, like preventing specific draw or dispatch to actually happen. Then making a capture and checking that it hangs without the previous changes. In the past that helped me to debug hangs which completely hanged the system, without any recovery. By making a trace and keeping the call from being executed, I was able to inspect the shader and its inputs to make a standalone reproducer. That's all about RenderDoc. What else could we do besides inspecting the frame? Before even inspecting the frame, it is a good idea to use Vulkan validation layers to find whether the application violates the spec, and there is no point in investigating further. Validation layers are the easiest way to find Vulkan misuse and should be the first thing you would try. However, not every error or warning corresponds to a real issue, and it may be hard to distinguish them. Thus, I could tell which places to check first with RenderDoc. Some useful validations are in the warning category, which isn't enabled by default. Make sure to enable it. The last option is to enable GPU-assisted validation to catch out-of-bounds issues in the shaders, if there are any. The driver itself could have ways to debug an issue. There are several debug options which are great to have in the driver. Option to synchronize every call helps detecting synchronization issues, saving a lot of time. Forcing the reemission of state for every draw call helps catching the issues with updates of the state. After that, you could bisect the state to find which one exactly causes the trouble. Forces the spilling for shader registers may be a crude way to check if issue is related to shader miscompilation or spilling itself. Substitution of shader assembly I mentioned before. Depends on the driver, there could be many more useful toggles. Now, what to do if we are unable to find the cause by inspecting the frame, but the capture at least reproduces the issue? If we are able to find the problematic draw call, we could attempt to make a standalone reproducer. Unfortunately, RenderDoc doesn't have a magic button to export the draw call to C code, or something like that. Though GFX Reconstruct is planning to support exporting a trace as a compilable code. For now, the only thing that left is to manually create either a number test or a standalone reproducer to mimic the call. RenderDoc allows to export buffers and textures in a binary format, so it's not that hard to do, but may take too much time and may lead nowhere. Without a way for an easy export, I think it's better to do this only as a last resort. Recently I had to do this for an issue with tessellation shader in Grand Theft Auto 5 on Turnip. It was impossible even to make RenderDoc capture to inspect the draw call due to the lack of RAM, so the only way to find out what's wrong was to write a reproducer. Here is the draw call extracted as a number test. It was much easier to work and experiment with. It also allowed me to run it on the proprietary driver and compare the results with Turnip, which quickly yielded a solution. To create a number test, I saved every buffer the draw call used and bound them with slots, offsets, and ranges I saw in the RenderDoc. It is a bit tedious, but easy to do. Aside from good old intuition, there are many more things to try. For hangs, you could inspect the GPU state which is dumped on the hang. Its usefulness varies between required and GPU vendor, but you could try. For shader yielding an unexpected result, it could be possible to instrument it and see what is really happening on GPU. That's not something that's available on open source drivers, though I recently made a prototype for Turnip, which I successfully used a couple of times. Another method to try is to compare the states emitted between your driver and the proprietary one, if there is any, and it does the work correctly. That is all. Thank you for listening. If I didn't elaborate anything, forgot to mention something useful, or you have any question about debugging, ask them.
Okay, thank you very much for your talk, Danilo, and now we have time for some questions. So, Baldur Carlson asks, have you tried editing captures for anything, exporting from to XML or zip? It's slow, but I've used it for debugging RenderDoc issues, which can be investigated in other ways.
I didn't know about this functionality. I knew that you could export to XML, but I never tried to edit and open it back. Yes, it sounds a bit tedious, but it could have saved me some time in some issues I had in the past. But yes, it sounds slow.
Demi Marie Abunur asks, is a cloud-hosted hardware available for any of those?
I'm not sure I understand the question.
Okay, can we get clarification? One moment, we'll just ask an IRC and hopefully we'll get some details. Okay, it looks like we won't get a clarification in time.
He's typing, they're typing. So probably there will be a clarification.
Yeah, most likely we'll have to continue on IRC then. Okay. Looks like there are no more questions for now. So thank you very much for the great talk, Daniel, and have a great rest of the conference.
Thanks, everyone.
Okay, and we're ready to go with the next talk of the day, Ray Tracing in Vulkan Part 2 Implementation by Jason Ekstrand. Take it away!
Hello all, welcome to XDC. I hope everybody is having a good conference. As announced, my name is Jason Ekstrand and I'm going to be talking about ray tracing. So I'd like to start off with a little bit about me. Most of you have heard of me by now, but if you haven't, my name is Jason Ekstrand. I am employed by Intel to work on 3D graphics drivers. I have been kicking around FreeDesktop since 2013. And these days I work on basically everything that's Intel graphics drivers, but not, I try to avoid OpenGL. So I work on a compiler stack, I work on Iris a little bit if I have to, I work on a Vulkan driver. Most of my focus is on Vulkan, but I also dabble in basically everything that needs dabbling. So last XDC, I gave a talk on ray tracing in Vulkan. I am not going to rehash everything in that talk. So if you are confused, feel free to go back to last year's and watch that talk, and hopefully that will help give you some of the background. I'm going to try to hit the major points, but I'm not going to go into detail about what ray tracing is or all of the details about how Vulkan exposed it. That was last year's talk. This year's talk is about how we go about implementing that in an actual driver. So without further ado, let's get started. So the first tricky bit about ray tracing is that it involves this concept of shader calls. As a quick recap, shader calls are, you have these special kinds of shaders called callable shaders. And when you create your Vulkan pipeline, you give it all of the possible callable shaders as one giant mega pipeline. Vulkan actually has a pipeline library thing, so you can do your compiles in pieces and then piece them all together. But the VK pipeline that you have to work with from the API point of view potentially contains all of the shaders. It's up to the driver how much compilation it does with all of them, but it's all available. When you go to do a Vulkan ray tracing dispatch, all the callable shaders that are going to be used for that entire dispatch operation are provided via a set of shader binding tables, or SBTs. This binding table is a chunk of GPU visible memory that has been filled out with shader group handles, which are queried from the pipeline. So you have your callable shaders, they come in groups, and then you query these handles, which is some 32 bytes of data, and then you fill out the shader binding table with that data. And the handles are what the hardware actually uses to figure out which one of the bazillion of shaders you have to go ahead and call. In any ray tracing shader stage, you can call a callable shader via the op-execute callable opcode in SPIR-V, which maps to execute callable ext in GLSL. To pass data between the shaders, there are variables that are decorated with a callable data storage class. There's actually two storage classes. There's callable data and there's incoming callable data. Callable data is the one used in the callee, or in the caller rather, and incoming callable data is the one used in the callee. And these two variables in the two different shaders alias each other, and that's how you pass data back and forth. Once a callable shader completes, control flow returns to the calling shader. So it's basically like a function call, only it's a shader call. So what do these actually map to in hardware? So for the Intel ray tracing implementation, we have this new thing called bindless thread dispatch. So in the compute walker command, which is the command that we actually emit into the command buffer to do a compute shader, there is a new bindless thread dispatch mode. And this mode does a couple of things. For one thing, it shuts off shared memory. There's no concept of a local work group in bindless dispatch. And there's also no concept of a local work group in Vulkan ray tracing. So we don't have shared memory accessible. The other thing it does is it generates a set of thread IDs one thread ID for each invocation. And these are used to track various things as you go through the flow. It also, I think, turns on some other magic hardware bits that make bindless dispatch possible. I'm not sure what all goes into that mode. Then each callable shader is represented by something called a bindless shader record. This is exactly your handle. The handle is actually made up of multiple bindless shader records. But you get a bindless shader record. And this is just a little bit of data that contains shader start address, SIMD size, and a local data offset. The bindless shader record is the bindless equivalent of a like our 3D state PS packet for setting up pixel/fragment shaders. Only it's for the bindless ones, and it's much, much smaller. And then bindless shaders can be invoked from either another bindless shader or one of these, or a compute shader dispatched with this bindless thread mode using the BTD spawn message. The BTD spawn message is a send message just like any other message in Intel hardware, which communicates with something outside of the EU. And it takes a few things. It takes a pointer to a bindless shader record. It takes the thread ID that was passed in. And it also takes a global memory offset, which I didn't, a global memory address, which I didn't say here. The thread ID is passed around explicitly for some hardware reason that I don't understand. In theory, the hardware could probably pluck it out of the shader itself somehow because it knows all that information, but it's passed along explicitly. And then to kill your thread, you emit a BTD spawn message with the retire bit set. So when you pass it the pointer to the bindless shader record, the bottom bit of that pointer is the retire bit. And that if that bit is set, then it ignores the rest of the pointer and kills the thread. And then when you do a compute walker with this new mode, instead of waiting for that particular shader to complete, it waits for all of the spawned threads to be retired. So there's a different termination condition that's also associated with that mode. And that's it. That is our ray tracing hardware. It's really quite simple. And everything that we do in the Vulkan API has to be mapped to this. The shaders themselves are pretty bare bones, like I said. You have a thread ID, you have a global data pointer, you have a local data pointer. The local data pointer is the bindless shader record address of the bindless shader record that was used to dispatch the current bindless shader, plus the local data offset that was provided in the bindless shader record. And this is used for implementing some of the storage classes that we have in bindless shaders. It's useful to be able to get at your own BSR. And then, like I said, this is it. It's up to us to build the ray tracing API out of this primitive. Okay, hopefully that goes up. Okay, so how do we map this to Vulkan? So one thing to notice is that there's no BTD return message. There's no call stack. There's nothing like that which we have available to us. This is the bindless shader call is the bindless spawn is the only message that we have. So we have to manage the stack ourselves. I don't know why it thinks I need subtitles. I hope that goes away. We have to manage the stack ourselves. This means we have to spill and fill around shader calls. Anything that's on the stack we want accessible after the shader call, we have to spill. We have to stash any return address, the return bindless shader record address, and any call parameters. All that we have to do ourselves. We then use the BTD spawn message to launch the child shader. And when we go to return, we have to BTD spawn to launch a return shader. And then we have to deal with all the stack unwind. Importantly, we don't have a return that returns back to the original shader binary. It actually invokes a whole new shader. This means, a second, let me see if I can kill my subtitle, kill this subtitles thing. I don't know. Nope. Oh. There we go. Thank you. Okay, so how do we actually do this? Let's say we have a simple shader that calls one other shader. So we have the shader main, it does some stuff, it calls a shader child, and then it does some more stuff before it ends. We have to change this into what in functional programming is called continuation passing style, where we start off with our shader, we split our shader main into main 0 and main 1, where main 0 does its first bit of stuff, pushes the stack, pushes the bindless thread address of main 1 onto the stack, and then spawns child. And then child does its stuff, and then it pops the return address off the stack and spawns main 1. Or spawns whatever that address is, which main 0 put it onto the stack, put main 1 onto the stack. So the thing that gets spawned there is main 1, and then it pops the stack, does its stuff, and then does the retire. So we end up splitting main 0 into two different shaders, one which does the first half and then does the call, and then the second shader does the second half and then retires. And then child gets called into, and then it looks on the stack to see where it should call when it's done, and that's how we get to main 1. So that's the way that returns are handled. This is obviously the most simple possible case that you can imagine of a single shader that has no control flow and calls a single other shader. So what happens if we have control flow? There is code for this. It is complicated. If ladders are pretty easy to imagine. You can imagine sort of getting back into an if ladder by just smashing all of the if conditions to the previously known values for that continue point and letting the if ladder collapse. That's not particularly difficult. Loops get tricky. Nested loops get even trickier. I'm not going to try to go into all of those details because see also the emoji. But it all can be done. It can be done with structured control flow. We have a pass for it, which if you are interested in those details, I recommend you go read the code instead of me trying to go through it in PowerPoint slides because it's going to be much more clear that way. This pass that we have is called no lower shader calls. Originally, I wrote it to be kind of Intel specific, but then Boss wanted to use it for RADV, and so he pulled it out and he generalized it a little bit. It was already fairly general. We just had to tweak things a little bit. This pass has two new no-intrinsics. It has RT execute callable, which is different from the execute callable that you get out of SPOV, because we want to be able to sort of denote the things that are happening before and after the lowering. This takes a shader binding table index and a pointer to the payload. It's assumed that the shader binding table is magically bound somewhere, somehow. And then we have an RT resume. And this is more of a marker than an instruction. So this marks the resume point. We use it when we are in the middle of the lowering pass to mark all of our resume points. We also use it afterwards to give us a shader that then gets lowered into a stack pop. But it really doesn't do anything. It's more of a marker than anything else. Both intrinsics have a pair of constants associated with them. A call index, which is the call in the original shader that this pertains to, and a stack size, which is the size of the stack in bytes at that shader call. And these are important because when you have everything split into 16 different shaders, because you've got a bunch of different calls at different points and you have to split everything up, having this call index helps you track which thing goes where. And the stack size is useful for the push and pop operations. The input of no lower shader calls is a single no shader. The output is as many no shaders as is required for the function, the call return handling. Then once we've done that, then we have a new pass, BOW no lower RT intrinsics, which lowers those no intrinsics into Intel intrinsics. So when we see the RT execute callable intrinsic, we do a few things. We place the return shader, finally shader record address, and the address of the payload on the stack. Those are treated as sort of the first elements of the stack of the called shader. And then we modify the per thread stack offset, so we push the stack. In our scratch memory for ray tracing, we have a small area called the hot zone that contains a few different things. But one of the things that it contains is a per thread stack offset. And so we modify that offset to push the stack, and then the called shader will read that offset to figure out where the stack is. We then insert a BTD spawn message to start the callable, but the BTD spawn doesn't actually kill our shader, and because shaders operate in waves, where you have multiple invocations going at one time, we might not have all of the invocations calling that particular callable. So we can't just kill the whole thread at that point. We go ahead and do the BTD spawn, which schedules the next shader, and then we do a no jump halt, which causes all of the currently active invocations to jump to the end of the shader and wait for the shader to end. Any inactive invocations will go on to the next else or break out of the loop or whatever it is that those invocations are going to do. And they may end up calling other shaders at other points inside of the shader that we're currently in. But we have to kill the currently running invocations. Then we do so that takes care of execute callable. For RT resume, mostly all we do is we read and modify the per thread stack offset. So we pop the stack. But again, it's nice to have that RT resume because the RT resume carries along with it the stack size, so we know how far to pop the stack to get back to where we want to be for the resume shader. So that's the basic flow for how we deal with the stack. The next thing we have to deal with is callable shader I/O. So in Vulkan, you have 3 new types of I/O that are added for callable shaders. You have callable data KHR, which is a block that's passed to the callable shader. I mentioned that earlier. You have callable data KHR in the caller, and you have incoming callable data KHR in the callee. And those 2 blocks are supposed to alias each other, and that's the way the data is passed up and down the stack. So the way we do this is that the callable data KHR stuff, whatever that struct is, it goes on the stack somewhere, and we pass a pointer, and in the SPURV, there's a pointer to that block that gets passed into the op execute callable. And then we pass it on down the stack. Incoming callable data, like I just said, it only exists in the called shader. It aliases the callable data block passed to op execute callable, and you can read to get data from the caller or write to pass data back. So we don't have like return values. You just write data into the callable data block. And then we also have shader record buffer KHR. And this is basically acts like a little UBO that is placed right after the shader handle in the shader binding table. So shader binding tables, when you pass them into the API, you pass in a base address and a stride. And the stride may be bigger than the 32-byte handle size. Any data after that 32-byte handle shows up in this shader record buffer KHR binding. And this allows the application to not only have shader binaries associated with a handle, but also have some amount of data so that they can do their own sort of post-shader generalization stuff. Maybe you want to use the same shader for multiple different types of hits, just with a slightly different texture index or something. And so you can accomplish that by placing data inside of this range that happens after the current handle before the next handle in your shader binding table. And that's accessible via shader record buffer KHR. So how do we implement these? So first thing we do is we lower each of the variables. So for callable data KHR, we just convert it to no var shader temp, and stuff it on the stack somewhere. And we don't actually have to do anything to stuff it on the stack. That'll kind of happen automatically when we assign variable locations. For incoming callable data, we look at each variable dereference in the callable shader, and we replace that variable dereference with a cast from the pointer payload, the payload pointer. And the payload pointer, as I said earlier, has been stored as the first little bit of the stack of our shader, so we know where that is. We grab the payload data pointer, we cast it to a deref, and we replace each of the variable dereferences that point to an incoming callable data with that. And in this way, we've tied the pointer in the callable data that came from the Novar shader temp to the pointer in the callee. For shader record buffer, we do basically the same thing. We replace a variable dereference with a cast from a pointer, but this time we use the local data pointer. So a few slides ago, I talked about how we have this local data offset in our bindless shader record, and we use that. And then one of the things we get in our bindless thread payload is this local data pointer, which is the bindless shader record address plus that little offset. And that gets us exactly to the shader record buffer data. It's pretty nicely designed for precisely this kind of API. Once we've done the variable lowering, which is mostly just a sort of search and replace operation on the node, then we can go ahead and assign IO locations, assign size types, and call no lower explicit IO. And that turns all of our IO into address calculations and global memory reads and writes, and done. All of our IO is taken care of. Okay, so that's basically how callable shaders work. It's a little bit complicated to get the lowering right, but it's not terribly different from what you would expect on a CPU, right? Everything's implemented in terms of goto. It's just that we have to deal with a few more complexities thanks to waves and not actually being able to jump back to the original instruction. But otherwise, all of the stack push and pop stuff is exactly what you would expect from, say, a CPU compiler. So how do we actually ray trace with this method? So ray tracing shaders work exactly the same as callable shaders. I started with callable shaders because they're kind of the building block that then gets generalized into ray tracing shaders. So with ray tracing, you have a few different kinds of shaders. You've got ray-gen shaders, which is sort of the base of your ray tracing shader. And technically, these are callable shaders. They may also be compute shaders depending on some hand-wavy details. You also have any hit, closest hit, miss, and intersection shaders. And all of these are callable shaders. So they're provided as part of your shader groups. You get handles to them. You create shader binding tables. You pass those in. And then based off of the different geometry indexes in the acceleration structure, when you hit a triangle, it will call the appropriate hit shaders based off of that stuff. Or intersection shaders if it's a bounding volume. If it doesn't hit anything, there is a miss shader that is provided as part of the op trace ray. And if it doesn't hit anything, the miss shader gets called. Instead of callable data KHR, we have ray payload KHR, and we have incoming ray payload KHR. Those are exactly identical to the callable data ones. The only reason why they're different is, I guess, because somebody decided they needed to be different. We probably could have made them the same storage class, at least as far as our implementation is concerned. And then op trace ray kind of maps to op execute callable with some extra stuff. So it's like execute callable in the sense that it does execute callable shaders, but instead of executing a particular callable shader, it goes off and traces an acceleration structure and executes a bunch of shaders depending on what it hits. Let's start with ray-gen shaders. So ray-gen shaders are specified to the API as a single element shader binding table. So you do have a shader binding table. You have to go fetch some memory to figure out which RayGen shader you're looking at. And then we dispatch it with BTD spawn like any other bindless shader. So the way that CMD traceways KHR actually works is we first launch a trampoline compute shader. And this is just a tiny little shader that all it does is it loads the RayGen handle. It sets up the per thread scratch space. So each thread has, we need to initialize the stack offset to 0. We need to set up the launch IDs, which also go in that hot zone that I mentioned. So the hot zone is per thread, the launch ID, which is a 3-dimensional ID, and the scratch offset. So we have to initialize that data, and then launch the RayGen shader with BTD spawn. If you can do some analysis and figure out that your pipeline only contains one RayGen shader or only contains a couple of small RayGen shaders, then it is possible to avoid that trampoline and compile it straight to a compute shader. This saves you a little bit of BTD spawn overhead. Probably not a whole lot, but it is possible to do that. But from the API perspective, it is fundamentally a bindless shader. It's not a bound shader because the ray tracing pipeline can contain more than one of them, and it is passed in through an SBT. So op_traceway is similar to op_execute callable. It has exactly the same shader splitting and conversion to continuation passing style that op_execute callable does. It has exactly the same I/O lowering, modulo the renaming of the storage classes, and it's really very similar. The biggest thing is that it doesn't just call a single shader. It actually interacts with the ray tracing hardware that we have. So different ray tracing implementations are different. At Intel, we have dedicated hardware for doing the ray trace operation. And the way we communicate with it is we set up a hardware ray data structure, which, if you are familiar with the ray query extension, is basically a ray query. In fact, it's exactly the same thing that we use for ray query, only where we place it in memory is a little different because of details. This acts as an iterator for the ray tracing operation. So think back to your early computer science classes. We know what an iterator is. It walks over a data structure. It points to the root of the BVH, which is the acceleration structure. It contains all of the useful stuff like your ray origin and direction, your hit shader tables, your miss shader pointer. All of that stuff is contained in this ray data structure. So once we've initialized the ray data structure, then we invoke the trace ray to do the actual trace. And it goes off, and there's hardware that just magically crawls through the BVH and figures out what gets hit and invokes the various hit shaders. This is very different from the AMD implementation, where everything that I just magically hand-waved away has to be done in shader code. They do not have hardware for crawling the BVH. They have like a couple instructions to accelerate ray triangle intersection, I think. But we have dedicated hardware for it. So I just call off to the hardware, and it goes and it does its thing, and then it invokes some more shaders. So how do these work? So hit and miss shaders are just callable shaders. There's nothing interesting going on. When we have any built-ins like ray origin, we just look at the ray data iterator and we pull the information out. We stuffed it in there when we executed the trace ray, and now we can pull it back out. If we're looking at something like ray geometry index, that comes out of the BVH. We have to, sometimes there's stuff in the ray data iterator that lets us get at the BVH thing that got hit, and so we do that and we read it out of the BVH. And that's the way we get most of the built-in information. Any hit shaders are kind of the same. They have the same built-in stuff where they pull it out of the ray data, the geometry index. But the any hit shaders don't actually return up the stack. And the reason for this is because the hardware might call any number of them. So we can't actually return back up to the calling shader until we have actually gotten to the end of our traceway. And so the any hit shaders, they just do their thing and exit, and then the ray tracing hardware continues. The one edge case here is if somebody calls op terminate ray, then we do actually return up the stack. Because at that point, the ray trace operation is done. We want whatever stuff came out of that any hit shader. Closest hit and miss shaders also return up the stack. So at the end of the traceway operation, we either hit something or we missed. If we hit something, closest hit gets invoked. If we miss something, then the miss shader gets invoked. And in either case, we return up the stack. If for some reason none of those get invoked, we have a trivial return shader. And this just returns up the stack. So sort of going back to, we talked with the callable shaders, stack returns were easy. You get to the end of the callable shader, you return up the stack. Awesome. With a ray trace operation, though, it's not so simple because you have so many different shaders that can get called. And so we have to have this complex strategy to make sure that one and only one shader does a return. And that's handled by closest hit or miss or the trivial return. There's also cases in hit shaders. But that's why we have to do this whole dance, is because we have so many different shaders that can get invoked. We have to make sure that return happens in exactly the last one. And again, there's code for this. You can go read it. Intersection shaders. So intersection shaders don't exist. That's a little tongue-in-cheek, but it's also really kind of true. So intersection shaders are what gets called when you have an AABB. And AABB stands for access line bounding box. There we go. And this is the sort of procedural geometry that you have in your acceleration structure. So your acceleration structure has two kinds of things. It has triangles, which everybody knows what triangle is, and then AABBs. And these are used for sort of procedural geometry, where the only thing you put in the acceleration structure is the bounding volume, and then an intersection shader gets called, and that computes the hits. In hardware, though, intersection shaders aren't really special. They're just any hit shaders for access line bounding boxes. There's a few dispatch details that are slightly different, but basically they're just any hit shaders. So when we get an op report intersection, which is where the client has said, I have computed an intersection value, here you go. When we get an op report intersection, we set up the hit, and then we call the any hit shader. And that can be just a callable shader. We don't, but I'll get to that in a second. And then when we get to the end of the any hit shader, depending on what hits we may or may not have gotten, we either report the hit or ignore the hit. And when we report the hit, that's just like if any hit shader for a triangle accepts the hit. And that doesn't necessarily mean that this is the hit. It just means that this is the hit that we know about, and then it goes into all of the closest hit calculations, and we take the minimum distance and invoke the closest hit shader just like anything else. But so I said they could be a callable shader, and they look kind of like callable. I said that any hit shaders could be callable shaders, and they look kind of like callable shaders from an API point of view. But we don't actually use callable shaders for any hits for AABBs. The API requires that they always come in pairs. So when you create your pipeline, you create a set of shader groups, and the groups are what you actually get handles for. And in the case of AABB geometry, the group is any hit shader, an intersection shader, and a closest hit shader. And you are guaranteed that the any hit shader and the intersection shader always come together in the pipeline. And we can use that to actually inline the any hit shader into the intersection shader. We have a pass for this. It's called BOW no lower intersection shader. If somebody wants to use this in another ray tracing implementation, it is not particularly Intel specific. I just put it there because I didn't want to have boss have to go out and review it. But this allows us to avoid all of the callable overhead for the any hit shaders in AABB geometry. How much is that overhead? I don't know. I've never actually tested it with callables, but inlining the callable into the intersection shader allows us to avoid whatever overhead is there. And it means that you can fairly freely set up lots of potential hits and do your any hit shader without worrying about the ping ponging. So there we go. That is most of the shader stuff. And I am actually, let's see here. How much time do I have?
Okay, you still have a few minutes, so let's go. We still have time.
How many is a few?
About 9.
Okay, I'm not going to get through BVH building in 9 minutes. I'll hit a couple of highlights. So the other thing that we have to do to implement ray tracing is building our acceleration structures. And acceleration structure, what we use for our acceleration structures is called a BVH, or a bounding volume hierarchy. If you watched my talk from last year, you may remember this slide. So let's say that this is our scene. We've got 3 things in the scene. We've got a cowboy, we've got a cactus, we've got a cow. And we want to be able to ray trace this scene. But we don't want to have to walk over every single triangle every single time, because that would be horribly slow. So what we do is we build this data structure called a bounding volume hierarchy. And what a bounding volume hierarchy is it's a tree-based data structure where you split the scene up into these sort of areas, and then each element of the tree knows the bounding volume of it and its children. So in this particular case, we have the root of the tree, which contains the entire scene. Level 1, we've got the cowboy, the cactus, and the cow as separate things. Those each have a bounding box. That's in red. And then at level 2, inside of those things, then we have a bunch of other stuff. And you can imagine that there's more and more levels going down to individual triangles. And then when we go to trace array, we can fairly easily eliminate everything from the scene that the ray doesn't intersect, or at least doesn't intersect the bounding volume. And this allows us to do the ray trace operation much, much faster without having to walk over everything. So how do we actually go about this? To bring up the driver, we built a BVH builder on the CPU using Intel's Embly library. Embly is an open source ray tracing framework. It's maintained by Intel. It's on GitHub. You can go look at it. Basically, what we do to build the BVH is first we parse all the Vulkan data into a set of into bounding volumes. So we look at every triangle, we compute the bounding box. Then we invoke Embly, and it goes and it sorts all of these bounding volumes into a BVH, and it has spatial algorithms to try and figure out where different stuff goes. I'm not going to go into those. And then we read the Embly data structure, and we write out the hardware data structure. This was not exactly a production-ready implementation, but it did have a lot of advantages for driver bring up. For one thing, it's much easier to see what's going on in your BVH if you can look at it from the CPU. You can fire up GDB, just poke at stuff. And it sort of lets you bring up ray tracing pipelines and GPU BVH building as separate things. It also is really nice if you have to deal with a hardware simulator, which I was dealing with for a while, because trying to do a GPU BVH build on a simulated compute shader is just not a thing that you want to do. We've got an implementation. I think I did post patches for it. It's not really production ready. It spawns threads behind the client's back. It doesn't tie into deferred operation. It's not optimized. It's not something you actually want to use. But when you're trying to bring up ray tracing on a driver, it's a really nice way to do the bring up. It just takes a lot of the variables out of the way for you. But no one cares about CPU BVH builds. Don't tell Zach I said that, but I haven't seen an app that really wants it, and DXR doesn't have them at all. And so, like I said, not going to talk about BVH building algorithms. We have to be able to build them on the GPU. So how do we do this? I'm going to try and go through it very quickly. I would like to talk to a few people about this later in maybe a breakout session. So I'm just going to hit it at the 1,000-foot view at 100 miles an hour, and we'll see how it goes. So the way we do a BVH building is we have a bunch of kernels that are written in OpenCLC. We wrote them in OpenCLC because it's easier to develop and debug that way. And we were going to share the kernels between Vulkan and D312. So there wasn't really a common format anyway. Might as well do it in what's easy for developers. Inside the Mesa patches that I have, we compile these at build time and embed them into the driver binary. I wrote a little Intel CLC build tool, which is based off of all of the same OpenCL stack that Carol and Jesse and Boris have been working on. It does OpenCLC into SPOV using LLVM, SPOV into Node into the Intel backend, and it kicks out a binary. And then we've taught the Vulkan driver how to dispatch those kernels. Unfortunately, BVH building is complicated. And we don't have just a single OpenCL kernel that goes off and does BVH build. Instead, we have a bunch of kernels that have to be run back to back. And to run those, we have this thing called a metakernel. So the different kernels have to do different things. So we have to initialize some data. We have to parse the API data, run sorting algorithms, dump out the hardware BVH. It's much the same process that we used for the CPU build, but it's done on the GPU. But they might be dispatched with different workgroup sizes. They might have different numbers of dispatches. The number of dispatches might not be static, and so forth. So we have to have this meta kernel to manage it. So we developed a meta kernel language called Grill. This executes on the command streamer, or the command buffer executor thing. It's able to read and write values from memory. It's able to do some basic arithmetic, some control flow, and then it can launch a kernel, possibly within direct dispatch, so that it can manage all the different kernels that we have to fire off to the BVH build. We have a parser. It's currently written in Python, uses ply, does a tiny bit of optimization, mostly to turn nice human-readable typable things into something that's reasonable to actually run, and then it outputs a pile of C, which uses our MI builder thing, which is kind of like node builder for the command streamer. Then we have meta kernels. So somebody has to figure out how to launch the meta kernels. So we have code, and this code runs on the CPU, but which selects the BVH building algorithm, computes sizes of various scratch memory things, allocates memory for inputs, and then it launches the right meta kernels in the right order. Because of course we can't just launch one meta kernel per build; that would be too easy. So yeah, this is complicated at best. Should we have meta kernels? Okay, there's my joke slide. So sorry I'm blitzing through this so fast, but I'm trying to sort of get to the open questions because I would like to have some discussions with some other Mesa people here later. So we have a few open questions. One is, can we share code better with Windows? Currently, we share the OpenCL kernel source in the GRIL files, but we have different GRIL file parsers, different meta kernel launch code, different meta kernels. It's mostly because of impedance mismatches between the way that the Windows drivers are written and the way that the Mesa drivers are written. I didn't really want to duplicate all of the MI builder stuff with another pile of code, and wanted to sort of reuse it better. Wanted something a little bit simpler, but it does mean that every time we pull a new version of the OpenCL kernel, stuff potentially gets out of sync. Another open question is, can we put more stuff in the GRIL files themselves? I talked about these meta kernels. We don't really have a good way to show them. If we could pull some of that stuff into the GRIL files that we use for the meta kernels, maybe we could reduce some of that mismatch problem when we sync code between trees, or possibly even completely allow for almost complete code sharing. Unfortunately, probably come at the cost of GRIL getting a little bit more complex as a language. The other big open question is, how much can we share with RADV? Ideally, we'd like to share everything we can. We'd love it if we could make some generic Mesa thing that goes off and builds BVHs. But there's some open questions that I don't know the answers to, like, can AMD do the same command streamer stuff that GRIL requires? If not, how do we do that? How do we abstract binary BVH formats? Because maybe we don't want to use the same formats. Maybe RADV should just use the Intel BVH format because AMD doesn't specify a BVH format. So maybe they can just use ours. I don't know. There's a lot of stuff to talk about with the RADV developers. So hopefully we'll have the opportunity to do that sometime this week. Should we compile GRIL files to Node? Currently, we have a little Python thing that's hand-rolled that has a little mini IR in it. It does the parsing. It does a little bit of optimizations. Maybe we should just have a node backend that generates MI commands via MI builder. As much as I wish this were a joke, this is not the joke slide. I have seriously considered doing this. If we're sharing with RADV, this might actually be a good choice because they're going to need to emit a completely different set of stuff with their command streamer. And maybe just having it in an actual IR is a good idea. Again, lots of open questions. So I managed to get to the end of the slides in time. I'm sorry I had to blitz through the last bit, but hopefully you found at least the first 2/3 of the presentation to be interesting and informative. And I'm open for questions now. And before I finish up, I am required to tell you all that Intel is hiring, and we are looking for more 3D driver developers. So if you want to, please talk to me on IRC. I'm not required to tell you that. I want to tell you that we want more people on our team. We would love to have some of you join us. So with that, I'll open it to questions.
Okay, it looks like we don't have any questions incoming from IRC at the moment. So we're also a little bit over time, so we probably have to move on for now. But if you want to, please create a breakout session and share the link to Jitsi on IRC.
Yeah, I will try to do that this afternoon.
Okay. All right. Thank you very much for your... Okay, wait, no. Vinimo asks, when will be a good time to discuss BVH building?
Anytime while XDC is happening. We have SSA-based register allocation this afternoon. Tomorrow, I will try to schedule something.
Okay, and
hopefully not on top of the register
and
allocation.
next, Bas Nieuwenhuizen asks, any games running yet?
I cannot say that right now.
Okay, let's go. We are very over time, so let's move on. Thank you very much for your terrific talk, and have a great conference.
Thank you.
Okay, and that was Jason Ekstrand's talk on Vulkan implementations. Now, coming up after the break is the second workshop of the day, SSA-based register allocation, led by Connor Abbott and Daniel Schuurman. After yesterday's talk, this workshop will be for people considering implementing SSA-based register allocation or wanting to understand the ACO and Freedreno implementations. We can go more in depth with different strategies and heuristics used to optimize the register allocation problem if there is interest. Link to the workshop's Jitsi is on IRC. In parallel to the workshop, there are 3 talks, starting with Roman Gilk's KWin FT in 2021 in just a minute. Thank you. and we're ready to go with the next talk of the day, which is Roman Gilg's KWinFT in 2021. Roman, take it away.
Yes, thank you. Hi, everyone. I'm happy to have a talk today about a project I was working on the last 1.5 years. Basically, it's called KWinFT. And I want to give you an overview about what we worked on in the last 1.5 years and what's the current state and what the next steps are that we want to take with the project. So the name maybe sounds familiar to some of you already. So it's of course coming from the project Quinn. Quinn is the KDE's KDE Plasma's, to be precise, default window manager. Right, Plasma is the desktop environment for KDE, and Quinn is the exists since 1999, and since 2011 there's also a Wayland version of it being worked on. And me personally, I worked on Quinn since 2016. So you can see here the very first merge request I had for Quinn, which was about atomic mode setting and so on. Yeah, so it was in August 2016. So yeah, 5 years now. Maybe you also know me from the last XDC, which we actually had in person, which was in 2019. I held a talk there about Quinn. I gave you an introduction to it, an overview, and so on. So I was quite active in Quinn for a long time. So doing a fork now in 2020, so last year, was maybe surprising. And I want to give a few reasons in the beginning why I did this. But like it's a single slide, and I don't want to talk too much about it because it's better to look into the future. But I think it's important, right? Just because that's probably questions which are relevant for a lot of open source projects to consider. It's very much about project governance and so on the one side, and about long-term planning and how we want to find common technical directions we want to move forward with. So let me just quickly run down the slide, and then we go over to more technical things and future things to do in KWinFT. From the social and project organization aspect here, there's this idea that KDE community should be kind of anarchic, right? Like everybody has access to everything as a KDE developer and can push to everything. It's very different to like how usually open source projects are organized, with you have kind of like a maintainer who has only merge rights, right? Or you have a company behind an open source project where you then have an overlay of the internal company structure onto this open source project in some way or another. So in KDE, you don't have this. I have all this, and it sounds really nice in theory. But the practice is, of course, very different, because you still need to have some kind of decision processes, and then there is a power vacuum, so to say, then it's going to get filled one way or the other. And so there is, for example, in the part of that I was working on, there's a single company which has a lot of control. And so that was difficult for me. I was part of that company earlier as well, but in 2020 already for 1 year not. So as an independent developer, it felt to me at this time it's difficult to really do long-term planning for Quinn, right? So I didn't only want to do short-term things, which are also important, right? Bug fixes and so on, but I thought there must be a long-term direction for the project. So that I thought was difficult. And on the other side, having not a clear structure also makes it difficult to have to define development standards, and also to really ensure that everything is documented correctly. And another thing, which is not directly related to that, but also was something which was important for me. As I said, I was already at XDC 2019, so that was kind of an important aspect for me to have this collaboration and this work together with upstream. So there was it felt at least to me, like that there needs to be a change in the mindset how we see freedesktop.org or we see Upstream, to have it kind of a value on its own and not just giving things to us, right? So that's something I really wanted to see make different as well, and I hope I can do this with QNFT, or at least ensure that this mindset is more spread in the future. So there were also some disagreements on K technical directions. For example, I wanted to rely less on Qt, right? I think it's not necessary for these low-level developments and system-level things, and instead there are great modern C++ tools nowadays, and also use more Upstream or use more from the Linux sphere as well. Back then, there was also, I wanted to focus more on the Wayland session and also accept at least for temporary regressions, just to push this forward. That changed a little over the last 1.5 years. Of course, now it's also 1.5 years later. So now Quinn has also done a lot of work. The developers have done a lot of work on the Wayland session, and I want to push more into the direction of more robustness. So that's all to this slide, and let's take you through the first 1.5 years of what we did in QNFT. So the decision to start with QNFT with Repland, Repland is like a library to wrap libwayland. That was done in January 2020. And for the first months, I basically only worked on the CI, right? So I decided to go with gitlab.com because I already knew it from freedesktop.org, and I liked what I saw there from the UI and also the integration with CI. And I wanted to have a real good CI going, right? Why did I want to have this? Because I knew that in the beginning I would be very alone on this project, and so I had to be really efficient with my time and had to automate as much as possible. And CI with all the modern tooling which there are allows that, right? You can ensure that there are not, or at least only few regressions with changes you do by having CI pipelines run on your merge requests, having tests and having static analysis running and so on. And so that was something I worked the first few months on only, and not only the CI, but also increasing the robustness. Because if you want to have your master branch always clean, always have a pipeline running green on it, then you need to ensure that your tests with or without sanitizers, that they run cleanly through. And so that was something I did in the first few months. I increased the robustness of it. So then in April 2020, the project was officially announced in a blog post. Jumping in the future, right, regarding CI. So that's the current state, right, of the development tooling. Now we have everything what I just mentioned. And I'm pretty happy with the current state. But jumping back in time to 2020, when it was officially announced in April. Afterwards, I had to then fork 2 other projects out of KDE, which was Disman and KDisplay. The reason was that I couldn't get some interfaces in, right? That I had a merge request to provide integration with QNFT, but that was not allowed in. And so I had to fork these projects, right? So the original projects were libkscreen and kscreen. And nowadays I'm pretty happy with that. It was a lot of work, but the forks, I think, are really prospering. And so in these first few months after the official announcement, I did a lot of work on outputs as well, right? Output management and so on. So the idea with Disman and KDisplay is basically to manage your outputs, right? To the position, the resolution, the frame rate, all that. So this was a lot of work in the first few months to get this really well done. And there was the first release, 5.19, right? So the version numbering orientates itself at Plasma, right? The releases are always synchronized with Plasma as well. So in this first release, It was great to have the Manjaro project on board. They directly released a package for QuinFT, which was really great. So nowadays you can still get a Manjaro on Manjaro package for it. Just install it with Pacman. And on Arch, on normal Arch, you can get QuinFT from the user repository. After release, there was when an XDC. I just mentioned it here because I had a presentation at last XDC about Disman. So if you're more interested in Disman and KDisplay, this output configuration scheme, then take a look at this presentation from last year. After XDC, right, so these output things, all these output things were done, right? A lot of work was done, but then I decided to do a really big project. Like it was really hard and a lot of work as well. It was a windowing refactor. I come to that later. The windowing refactoring basically means that the heart of QuinFT, how I would call it, was being completely remodeled in a lot of ways. And the reason for that, I come to that later too. 520 release was in October last year as well. So that also went smooth. Then the windowing refactor went the whole winter. And for the 521 release, it was then basically in a good state to go live, right? So that was merged then. And after that, so we are now already in this year. After that, there was some more work done on multi-refresh support in the Wayland session, so that different outputs can run with different refresh rates, which of course is a crucial feature to have. And then there comes something interesting, right? I decided then to take a risk and invest all the available time into working on WL Roots backend for QuinFT. And about all the challenges there, the advantages, and why and how this will go on in the future, I will have a talk tomorrow, especially about the WL Roots backend in QuinFT. So you are invited to join this talk then as well. 522 release was in June this year, right? The WL Roots backend actually didn't go into 522 release. It was worked on a feature branch, and afterwards, then I could merge it. So now we had some time till the next release, which is scheduled for October this year, to stabilize it further. Right, it's working already very well, but to stabilize it somewhat further. More about that tomorrow as well. The last 1.5 months, or rather 2.5 months now already, I worked on several people. Luckily, I'm not the only one working on QuinFT, which is great. Worked on input, everything input related to QuinFT, which is necessary because Wayland Compositor handles input as well. And now we are at XDC 2021. All right, so that's from a retrospective on what we worked on in QuinFT. And I just want to come directly to the next steps, like what are we aiming for with that project, right? And just 2 points, right? So it's very straightforward, very simple. The major goals, right? There are, of course, many more smaller goals, right? A lot of feature work which can be done. But the major goals for 2021 and beyond are, for one, deeper integration with WL Roots. And I come to that in tomorrow as well, of course. Like, what does this mean? And on another point, the library split out, right? So join the talk tomorrow about the WL Roots backend on what the deeper integration with WL Roots mean. And now we're going to talk more about the library split out. From the timeline, though, I guess I want to start first with the WL Roots render. So that's the integration thing. More about that tomorrow. Now after XDC, I want to start with it and with the release in October then continue working on it. And till the next release. And then afterwards, I want to really start with the library split out. So what does this mean, the library split out? the idea is to distill reusable C++ libraries out of QuinFT. And the objective is to provide these libraries in a way that other projects, right, independent of QuinFT, anything, right, can build X11 or Wayland compositors with it. And there is a catch to it, or kind of a restriction I want to ensure is satisfied, that these libraries should only depend on VSTL, right? No Qt. And so if you want to build an X11 compositor, which frankly, of course, it's not a good idea anymore in 2021, but there are certain advantages why I think it's still reasonable to make this still possible. So then it should depend on XCB. If you want to build a Wayland compositor, then it should depend on WL roots and Repland, the library which we provide as well. What's with X-Wayland, you ask? Well, of course, if you want to support X-Wayland, then you must depend a little bit on XCB and so on. And that's also the reason why I think it makes sense to allow the creation of X11 compositors, because a lot of these things actually transfer very well from one to the other. So if you can build an X11 compositor with what you provide, then you can easily enrich a Wayland compositor with the parts you need to also support X-Wayland clients. Why? Because all the functionality which you need as an or the complex things you need as an XWM, like an X window manager, these are the same, right? So you need to provide them anyway, so why not provide them in a separate library so that you can then interact with transparently. But yeah, so that's the basic idea of the library splitter. So I announced this already last year, and there was one comment, yeah, if you want to do something big like this, why not start from a blank slate, right? So why not start on a without all the baggage of 20 years of Quinn, right? So just start from new, right? And there are projects which did this and which did this successfully, and it depends on the circumstances if it makes sense or not. So I don't want to say it's never a good idea, but there's just one quote I have to give you here, right? So it's from The Cathedral and the Bazaar from Eric Raymond, and it says, "Good programmers know what to write, great ones know what to rewrite and reuse." So I said, it can be also a good idea to just build something completely new, right? So it's not always the case that you should always reuse something, but there are advantages to reusing things and remodeling things instead of starting completely from new. And if it's only for dogfooding, right? So currently everything we have in QuinFT, we can use ourselves, so we can directly see if a change we do has a certain regression potential and then fix that, right? If you just start from new, you're probably not so much dogfooding your stuff. Right, so that's the basic idea of the library split out. How would this look then in an ecosystem? So the current QuinFT ecosystem, right, looks like this a little bit. So you have QuinFT in the middle, which is the binary which you can run and which is Wayland and X11 compositor binaries come from with it. It depends on WL roots for seed display input at the moment, right? More about that tomorrow. Repland, which is the library we provide to wrap the Wayland protocol thing. So this is where we talk with the Wayland clients. And Repland, of course, depends on libWayland. On the other side, if you look at as an X11 window manager or as a Wayland manager with XWM functionality, then QuinFT depends on XCB, and via the X11 protocol, it then window manages all the desktops and clients which there are. After the library split out, we have kind of like a library collection, right, where we have split out the functionality of QuinFT. So that provides then the logic and the integration. And we can have another Wayland or X11 compositor. So simple as that, right? And the idea, if you look to the bottom left, is of course to not only support in the end Plasma desktops, but be able to also have alternative desktops support, right? That's in theory possible via all the Wayland protocols that there are and which there should be. But of course, it still needs some time to really prosper this out. But I think that's really a long-term direction we should aim for. So for the library split out, the preparations, they are already ongoing for months in the background. So that's maybe not something that you see easily by just looking at, hey, what features or which fixes are there in the latest release. But a lot of time we decided to wait with a certain feature or to integrate a fix into a bigger change, which is with the goal of then having this library split out be reasonably doable at some point in the future. For example, I talked earlier about this windowing refactoring in the winter. And one big thing there, or one big sub-project in there was to unify the X11 and the Wayland logic in regards to windowing. So as an example, right, the XDC shell protocol provides means to synchronize the resizing of client windows. There is also an X11 extension for that. And actually, if you look at these two, right, so Xsync it's called and so on, if you look at these two mechanisms, they are not so different as you would think in the first moment. So over winter in this project, I just unified these really hard and put them together, the code paths, so that there is not so much difference, which there was as when the first time XDC shell support was introduced, the decision was made to not touch the old code, right? So there are different code paths. Now they are unified, so it's easier to maintain, easier to handle, easier to understand, right? Easier to understand is also an issue with the second point, code quality, right? So if the code quality, and with this I don't only mean like the logic, but also this code styling and, for example, in CI, running Clang format over that, right? The usage of modern C++ tooling and so on. So all these code quality aspects are maybe not so important if you just build a binary that should be run by users, but it's important if you want to provide a library which then should be reused by other developers. So that's also something we increased. And yeah, more STL. So STL is the standard template library, less Qt. As said, that's a requirement for these libraries in the future to not depend on Qt anymore. So over time, there's less and less Qt usage in the core stuff of QuinFT. But that's an ongoing project, right? You can't, of course, just do everything at once. Namespacing just means, in the sense of C++ namespacing, provide reasonable namespaces for things so that people who want to use these libraries can orientate themselves, and that you can use these libraries also a little bit independently, more to that later. So yeah, this windowing infrastructure, that was the project I did over winter, right? And as said, that was important in this aspect, even though it's not so directly, you can't directly see this if you look on it from the outside. Namespacing is one thing, relocating code is another thing. So that's also something I just wanted quickly to highlight, which was going on over the last few months, especially. So a lot of the code which we had is being moved into different subdirectories, right? So you have, for example, which didn't exist before, right? So for example, you have here this input directory, which contains most already, and I think it pretty much does all of the contain nowadays all of the input handling code. So that's input is only relevant as a Wayland compositor. So this input directory in the end should be the seed for kind of like this library, which is supposed to be then linked against by Wayland compositors which want to make use of it. Platform is another directory. It's kind of like an overarching entry point. Render, where in the end everything about rendering and effects and so on should end up. Rules is for window rules. Seed is for our session integration, which nowadays on Wayland works via WL roots and CD, which is nice. And Win is everything windowing logic, right? So there was, just to give you like a feeling for what kind of work there was done in the past few months and years in the background, which is not so directly, which you can't directly see that much. Yeah, so there's a lot of work going on for this project. So, but I didn't really talk that much about reasons for it. Why do we want this library split out? So there's one reason. We could use this avenue to share functionality again with Quinn, right? So the Quinn development is ongoing. They also do some interesting work there, also good feature work. But of course, it's just doubling the work, right? So if there's a future where QuinnFT again could be directly used by KDE users, this would be great, of course, right? And one idea is to do this through this library split out, then Quinn or the KDE compositor, default compositor, whatever it is in the future, can then link against these QuinnFT libraries and use selective components from it, right? It doesn't need to use everything at once, right? But there are maybe some things which are in a reasonable state so that it can be used. And of course, this means that although there should be no Qt usage in these libraries, that it should still be that still Qt applications can make good use of it, right? So that's definitely something I want to ensure too. I think it improves the robustness, right? Because you just have to ensure, right, for example, code quality, right? If you ensure code quality, if you ensure good logic, if you unify logic, that all improves the robustness. You have clear API interface and implementation difference, and so that I think this overall improves the robustness of the product. Yeah, help the ecosystem to prosper. If you provide libraries which other people can then use to build a compositor or enrich their already existing compositor, that's a great thing for our Linux graphics ecosystem. And I think it's like thinking a little bit in business terms, there's an abstraction gap in current libraries, right? So there's a market niche which is there to fill. Because you have currently two libraries which are relatively low level, so which you can interact with very much, right? You can use and shape them in ways which allow you to really access everything underlying. But they are very like they don't have that much abstraction, so it might be difficult to quickly get up a compositor running. And on the other side, you have two libraries, Mir and Qt Wayland, which are very much abstracted. You can easily and quickly get a Wayland compositor up and running, but it's difficult to then afterwards really access the underlying functionality. That's at least how I from what I've seen about projects, how I interpret that. And the QuinnFT libraries are meant to bridge this abstraction gap. And this should be done with selective compilation with CMake. So you can pick the libraries you actually want to use. A very well functional layering, of course, so you can access underlying implementation logic as well through namespacing of C++, and the aggressive use of C++ templates. So how would this look maybe in an example? So as a basic feature goal, right? So that's really where I want to get this in the end, right? If you want to build a Wayland compositor, then all you should need to do is something like this, right? You get a platform, you get the Wayland server from this platform, then you create a workspace, and then you should run this Wayland server. So that should be in the end what you have to do to get a Wayland server up and running with the QuinnFT libraries. If you want to enrich this with more features, for example here, Xvalent, then you should just get an Xvalent platform and you add a template argument to the windowing type you want. Right now, imagine you want this, but you want to use your own library with that together. Then you would link against your other library which you want to use, and you would change out the parameter for the template parameter for the template type for the window you want to use from your other library. So that's where these templates come in place, and yeah, that's the goal that we want to move into. And yeah, I think that could be a really interesting way for other projects to make use of it, and to also customize it then in ways and extend it in ways which they see fit. So the final abstraction span of QuinFT should then be everything above these lower levels, like I said, WL roots, right? If you want to build a compositor very with a low-level library, then that's something for WL roots, right? So that's also why QuinFT depends on it. But if you want to have some more abstraction and a library which helps you some more, then QuinFT is the QuinFT libraries are the way to go with it. So, and feature abstraction is the one thing, feature richness is the other thing. And of course, there QuinFT can really score, right? Because it's based on Quin. So Quin is one of the most feature-rich compositors that there are. So all these features that there are in Quin could then be opened up and can be reused in other compositors, right? And I just listed very few. It's so much which there is in QuinFT. So yeah, you know the project Quin, of course, and how KDE is famous for having a lot of features. So yeah, that providing these all these features with feature richness to the ecosystem is really something I'm looking forward. So that's the goal for the next few months, right? For the next 1 to 2 years with QuinFT. And the question is, of course, like how to achieve this. And so in regards to scaling the project, we are currently at the position that we have 2 full-time developers working on it. And there are also multiple independent contributors working on it, right? As said, as you can see, it's a lot of work, but we already achieved a lot. And currently the development is really the fast pace moving forward. It's great to have another full-time developer besides me working on it. And it's also great to have other independent contributors who want to learn and contribute and help the project grow. But there's still some Wayland-specific features missing at the moment, right? So this ongoing work on the fundamentals is fine, I think. But some Wayland features which are currently missing is input methods, right? So there's some work ongoing in this regard. There's also this upstream ticket to really unify it in the next version. So that is something which should then be considered. Graphical tablet support is missing at the moment. That could be probably integrated rather quickly. And Pipewire video streaming, that's something I really want to have in there soon. But it depends a little bit on this WL roots to render project, like in the next few months, like how, in which way it should be integrated. My goal for QuinFT is to have enough resources to have a team of like 4 to 5 full-time developers. I think that's the size where you can really, really accelerate the development and speed up the creation of these libraries. And yeah, very long term, after these libraries split out, then there must be some questions answered about like how should this be governed in a way, right? And of course, the easy answer there is like have a federation with maintainers, really good protocols and really good rules on how they can, what responsibilities they have and so on. And then these maintainers maintain different parts of these libraries. Right, so that's about scaling the project. So if you are interested in this idea which I presented today about this library split out, and you think that's interesting for you as a user or a developer, then support us, right? Contribute to our project. You can easily get in. Everything is documented in the open, right? And yeah, if you have a product or a compositor in the future you want to base on, then yeah, you can also contact us, contact me about investment possibilities and so on. So regarding the development, project organization, project home is at GitLab, right? So as I said, open development, there are some developer communities ongoing, and in the future, right, so at some point there should be an official homepage, but because it's very technical, I think we can go without it for now. And yeah, so as I said, regarding investing and so on, also, or donations, right? At some point, I want to found like a non-profit limited, something like that. So that's also something which needs to be done in the near future, I think. Right, so I hope you got a good view into the project, and I could show you some interesting things. So thank you for listening. And if you have questions, I guess now's the time, right?
It is indeed. We have 2 questions on IRC at the moment. Simon Sears asked, on slide 23, in this diagram, where would you put the KWinFT leap?
Slide 22.
23.
All right. What would I put there?
Where would you put KWinFT leap?
Leap?
Leap.
I think that's the other diagram, right? Where I then put it next to each other, right? So the idea is to be from the abstraction not as low level as WL roots, but above that. So but then encompass also Qt Wayland and Mir. What was the question?
Okay, I think that was roughly about that, yeah. Okay, and there was also one follow-up. What's the y-axis? Toolkit versus mid-layer?
Y-axis toolkit was...
On slide 23 and the one that you just presented.
Okay, yeah, this graph is probably not as detailed as technical-minded people want it to be. So toolkit versus mid-layer is a good it's a good good thing to talk about. And yeah, as I think I mentioned this in the past at some, was it in another presentation, or I think it was in a discussion with other developers from WL Roots and also upstream X.Org. So WL Roots has kind of a toolkit approach, right? Instead of a mid-layer like libwestern has. So there is you can more easily interact with the WL Roots internals, right? So if you so I would say WL Roots is more easily to get to a lower level. So maybe abstraction is not the right coordinate. Maybe it would better to like cost of implementation, right? So with Qt Wayland Mir, you don't have as much homework to do first to get something going. And but on the other side, you can't access it that much, the internals, right? Whereas with WL Roots, you can access it very well, the internals, but maybe you also have to do a little bit more work in the beginning, although you can also get at least a minimal compositor up and running quickly, like tiny WL shows. Right.
Okay, and we have one more question from Bitin. Wondering if things from KWinFT would be merged into the original KWin if they are deemed good enough to fit there.
Yeah, so that's not for me to decide at the moment. I think though that yeah, so what my current strategy is for that, right? Because it doesn't make sense to have for some time it makes sense maybe to do double work if you have different alternatives, right? Which both make sense and which you want to push forward and see which one in the end has more success, right? But long term, there should be a road to get some of these features back, right? For KDE users with the default KDE Plasma compositor, right? And so the idea with, or one reason for this library split out is to share functionality with Quinn, right? I think it's easier for the Quinn maintainers in the future to selectively link against certain functionality than saying at some point, okay, now we use, or now we merge all this code from QuinnFT, which of course is now very different, right? Also because of this library split out than before. But if you have these libraries, then, and as said, it's like my release schedule is aligned with Plasma, so that should be no problem. And I'm always open for communication, of course, to ensure that it's possible to make use of some of these libraries inside Quinn. So that's, I think, the strategy I would go for. Yeah.
Okay, then. Well, looks like that's all the questions we have for now. So thank you very much for your terrific talk and have a great conference.
All right. Thank you. Bye.
Okay, and we're ready to go with the next talk of the day, and that's Saiki Shorokonda and Ravindra Babuganapati are going to present us a talk about One API Level 0 Sysman. Saiki Shor, the stage is yours.
Okay, yeah, thanks. Yeah, this is Saikishore Konda. I'm working in the Intel, leading the level 0 Sysman efforts. Okay, so I will talk about One API level 0 Sysman today. The agenda, I will talk about like the introduction about One API and level 0, then what are the goals of the level 0, then I will talk Sysman architecture and what are the Sysman classes and resources. Then I will show some flow graph diagrams for init and resources. And I'll take some example, how could you use the Sysman by any tools. Then I will end with some Python based some CLI tool, show the example and demo, and end with the questions. Okay. Yeah, so the question is why one API? Like we have like diverse workloads, which requires like different diverse architectures. Like one architecture could not solve the heavy compute workloads. So it requires we need to have the mix of like scalar, vector, like matrix and spatial. So the future is like it's possible that we could use mix of this combination so that it could solve the problem of the heavy compute workloads. And currently the problem is we don't have one simple solution where like whether it's a CPU or GPU, they have their own programming models, and the application developers and middleware developers, they have to uh, modify or accordingly they need to adapt as per that. So that's why Intel came up with the solution like one API. It's a common interface and a common like one single programming model and language where application developers and middleware can use that which will interface with all the variety of accelerators like scalar, vector, matrix, and spatial. So that's why one API is here. So, okay, if you see the one API, the architecture, so it consists of the one API product, and underneath there is a level 0 software stack. So before talking about level 0, so one API uh, has the possible options like direct programming, or you can use the API based programming. So direct programming, like application developers who want to use they use the TPC++, and they have to implement their parallel algorithms. And whereas in the API based, like it has the libraries available where like mathematical kernel library, deep neural network, and like video processing library. All those libraries have inherent parallel programming available. And one API product will use the level 0 interface to work with the vector, matrix, and spatial combinations. So level 0 interface is the lowest level user space interface, which is the which gives the fine-grained control over the all the hardware accelerators, and it is divided into like three set of modules like core, tools, and system management. So core is basically for device discovery and command submission, synchronization, memory allocation, all the compute related work thing. And tools will be like for debugging, instrument programming, instrumentation, and metrics discovery. Uh, for this kind of work, tools will be there. System management is basically for managing the system for power and profile, and control the power and performance of the devices. Also, it will managing the devices for firmware management, like updating the firmware, or like running the diagnostics or device set. So we'll talk deep in about system management. Okay, so what is the level 0 API objectives? So basically, it is a single API. It want to cover all the vector, matrix, spatial compute. It's basically low level interface, and it will be give the high performance interface to the device, and it has a very fine grained control over the accelerator capabilities. And it is first of all open source, and it is standardized, and any vendor, like any third party vendor, also can use this open source code, and they can develop their own driver and for any type of accelerator, and that is welcome. And basically it is started with a GPU, has influence with the GPU architecture, but it could be expandable for scalable for other set of hardware architectures such as FPGA and other accelerators. Okay, so we'll talk about level 0 sysman goals. The basically level 0 sysman is for monitoring and controlling the power and performance of the devices, also monitoring the health of the device, and it could do device reset and update the firmware. It could monitor the RAS errors, and also it could driven event driven. If any device health changes, it could act it to the corresponding client which is using the level 0 sysman. Also, it interconnect with the peer-to-peer, manage the peer-to-peer interconnection on the fabric if multiple devices are connected. So those are the set of the goals. And security perspective of the level 0 sysman, whatever the device modifications controls, those are like imposed at the OS level. I mean, nothing like level 0 will impose. It's all imposed by the OS layer. Whatever the privileges, admin privileges. Basically, you require the rootfs for some control operations on the devices, like for writing permissions. So this is a sysman like a typical users where sysman API can be like in a server platform. There could be possible to run a daemon where you could control and monitor multiple GPUs connected in the server platform, and so also possible in the client products. You can end user can use the GUI based client developed using the on top of the sysman API, where it can graphically display the power, temperature, and other set of options to the user, and they can control and they can read the different things. Also, within system administrator, also they can use the using command line tool. So control will go from up and down, and all the telemetry will be only readable. So control is only writable thing. Okay, the sysman architecture diagram in generic any OS specific. So I'm not. It's like generic thing. I mean, I'm not talking about any Intel or anything. It's generic architecture diagram. So where level 0 sysman is part of the level 0 library, which has inherent core tools and sysman. And so this level 0 sysman will talk to the a different set of KMDs. Like PCI bus driver is for device reset and getting the PCI BDF information, PCI bars information, and PCI throughput information. It can use the voice specific PCI driver. And other set of KMD drivers is for accelerator and any system related function system KMD driver, and telemetry like power, temperature, other telemetry information will be accessed through the telemetry KMD. So this is the like general typical sysman architecture diagram. And yeah, these are, like I said, Intel device drivers, but it could be any vendor. They can develop their own drivers. Okay, sysman API, like I am typically divided into different set of classes where there is a cluster of power management and workload management and system management and reliability and hardware event and scale out. So I will talk each of the API very high level. The frequency API provides what are the available frequencies, whether it is GPU in the system or the frequency type for any memory or like as HBM, and it can give the control to set the min limit and max limit. Also, it can read like what are the current frequency is set to, and what is the current actual frequency set, and you want to set any frequency you would like to set from the given available frequencies list, which is provided through API. And also it has the TDP frequency, like what is the TDP max frequency which can support. And if suppose the frequency is throttled any of the reasons because of the heating or because of the high power, so it will give the reasons why it is the frequency was throttled. So all those will be covered on part of the frequency API. And the power gives the GPU current power is consumed, and what are the peak power and what are the burst power and what are the sustainable power. Like peak power is the instantaneous power. When it is measured, it can check how much is the instantaneous power, and if it is crossing any threshold, it's always possible that we could throttle the frequency. Similarly, burst power is like average over 2 millisecond measured this power. It's called PL2. Similarly, like sustained power and around 28 millisecond, this is calculated. And user can always set limits and get limits. Also, user can have register for event if any energy threshold, like whatever the energy consumption by GPU is crossing some certain limit, he could get notified. So that's possible in the power management. And standby is like by default, if device is not doing any workloads, so it can put into standby mode. But it's a costly, like if it goes to standby mode and then comes back from sleep to consume. So it's possible that for user can disable the standby mode. It can set to disable. Those options will be in the root permission level. And temperature, like it will measure the temperature across all the sensors, and it will give the max temperature within the system. So that way we could measure all the power related functionalities. And when talks about workload management, the sysman will measure the engine utilization. Basically, how much engines, like there are different type of engines like compute engine, copy engine, render engine, and other set of engine. When some workload is running, what is the engine utilization in a time window? It will give those information. And there is a performance factor where if you want to tune your workload only compute base or memory base, so it has a factor of 0 to 100. So if you set it to 100, you could give more energy driven to the compute oriented work, so that memory will give only 0. But if there is any memory oriented workload, we could always give the factor to 0, so that we could get throughput faster. Throughput is less from the memory oriented workloads. And scheduler, if there are multiple workloads want to submit the command queue and use the common hardware resources, there are like different scheduler modes, like uh, scheduler slice mode and scheduler exclusive modes. Like slice mode is, it will given a time, in a time it will share like in each time one work will be given, and then after timeout will preempt, and another task will be given. And there is a like timeout mode where you can always set timeout till what time the workload will continue, and if any high priority work will come, so after that timeout it will preempt it, and the other workload will be run. In exclusive mode, like no other workload will be run until that current workload is completed. So those kind of modes you can always use, so that you can manage your workload. And memory, so this API will give what is the current free memory, and what are the bandwidths, and what are the read counter, write counters within the system. So it could use this information. Memory of not only like HBM memory module, it could give the cache level or L1 L3, those details, memory sizes, where those inputs can be used for optimizing the performance oriented compute workloads. And the system management, the device functional will give the like device serial number, board number, and device unique identifier. And it could also have the some set of APIs where you could say device need to reset, or if the device got wedged or device got repaired. So those information will be available within the device. And the firmware, it will give all the firmware are present within the system. It will give each firmware information and what is the firmware version. And you could also flash the specific set of firmware where you want to update the firmware. So that's possible with the sysman. And fan, PSU is like basically controlling the fan and power supply unit. Also, it comes under part of the system management. Now let's talk about reliability management. The RAS are the one of the critical feature for sysman, where we could always important for if device is encountering different set of errors, like it's correctable errors or uncorrectable errors, to notify to the application. And if uncorrectable error keep coming and the device is going to in a unreliable manner, so it's always possible that a user can take action to reset the device, or user can run the diagnostics. So diagnostic is like self-test where it can run the device function, device stability. Is the device stable, or if device need to get repair or not. So while running the diagnostic, we need to stop all the workloads. And when you run the diagnostic, it will either give no errors, or it could give that it could get about that, so that you could not use the device. You need to remove from the card, or it's possible that quite possible that some of the hardware repair occurred. So once repair occurred, you need to reboot to get back to the original condition. And the other thing is the event management. There are like set of events. Sometimes device reset, for example, device need to reset. When you run the diagnostic, it will set the device reset event generated. Once the device reset event occurred, so application need to reset the device. Also, there are other errors like when temperature cross threshold, or power cross threshold, or RAS errors cross some threshold. So those will be notifying to the client. So basically, client have the register API. All the devices which are interested to listen for some particular event, they can register those events, and the listen will be at the across the system level. If let us say if multiple devices are there in this host, which are connected to host, we could listen to listen at one point from all the devices. And scale out management is like if we have connected fabric to the multiple devices, and it could possible that sysman can enable disable particular port, and it can also check each port configuration information. What is the current transmitter current and receiving transmit speed. Also, it will check the what is the remote port ID and what is the current remote fabric ID, and it's possible to bring all those information, and you can create what is the topology looks like, how all the devices are connected to the fabric. So these are the overall system classes in the Sysman API. So I will take some examples using the Python CLI, and I'll see how the field look like of those APIs. Okay, the Sysman init code example. If somebody application want to use the Sysman, and they want to call those set of APIs, so what is the installation code looks like? So they need to set an environment variable JDS enable Sysman has to set to 1, and there is a main code where JDinit initialize all the devices and all the drivers in the system. So once installation happens, then we'll call driver get. So we'll find out how many drivers are there in the system. Based on the driver count, we allocate those many driver pointers. So for each driver, like example, if in a typical host machine, if you connected, let us say Intel GPU and NVIDIA GPU, so let us assume that NVIDIA also has supported level 0 driver. So it's possible that we could read for NVIDIA driver and Intel driver also. So for each driver, we could check like that how many devices are connected. For one driver, we could have multiple devices. So for each device, we'll get all the allocate the memory and all devices. And for each once we allocated for all devices, we'll read the properties. Currently, we are only supporting for if it is device property type is GPU, because level 0 is like generic. It could support for GPU, FPGA, and other accelerator. But right now, we have only limited to GPU. So if it is not GPU, just we return. And if it is GPU, then only we need to typecast to the Sysman device, so that you will get Sysman device handle and use this Sysman device handle for the rest of the Sysman APIs to get the power, temperature, any like telemetry or any kind of information you're looking for. So this is the example usage of the Sysman code. And let's talk about in the flow graph how the Sysman execution diagram looks like. So when application want to use the Sysman, he will initialize through level 0 loader. So loader will load the basically level 0 library. Sysman will be inherent of the level 0 library, and this library will call actal to get all the device queue properties and initialize all those data structures of the each and every XP device, and whatever the manageable resources like temperature or telemetry or strict scheduler, all the classes resources will be initialized, and it will be stored in the device data structure during the installation. This is how init will take place. So once it is done, if you need to access those class resource properties, like if you want to read the what are the power properties, or if you want to read the frequency properties, anything, first we need to call the enumerate devices and get the core device handle, and core device handle you typecast to the sysman device handle, and then call enumerate resources. So basically you want to look like what are the modules, or what are the class within the sysman library are supported. So it will go and check all the types of the sysman resources, and it will return those handles. So based on those handles, you can get the properties where you want to read the resource properties through sysman library. So this way your resource execution getting resource property can be read. Okay. Uh, then there is a one use case I want to talk about, like in a GPU, there will be like temperature is crossing like 100 degrees centigrade, and we want to check how the how can application can write, and how can you control the by reading the temperature, how can you control. So that is a use case I just explained here. So client will call initialize the sysman, then client will call enum temperature sensor, so that it will find out what are the temperature sensors. It's go and read all the temperature modules through telemetry KMD, and it will whatever the sensor handles, it will return back the handle status. So once handle back, we'll call the temperature get state. So this temperature get state will read all the temperature from the sensors from the telemetry module, and it will collect all the temperature sensors from various resources, and will return back what is the max temperature occurred in the device. And if we observe that there is a certain like crossing 100 degrees or something like that, we process the temperature, we could take action based on the temperature. So what I'm doing is I want to control the frequency so that it could cool down. So that I will find out like what are the frequency domains available in the system. So it will call the accelerate KMD, and it will find out what the frequency models are available, and it will return back the those corresponding frequency models handles. And by using those handles, I will call like what is the current range it's set. So it will read current what is the ranges from the driver. So it will get those frequency ranges, and we could set range to lower limit so that the temperature will be cooled down. So this is the like one of the example use case I could cover. We could do multiple things. Okay. We have Python command line interface tool. This is basically it is a reference implementation. It is available as an open source code. It is used to for query and control the system within the system. It can print different like simple std out, print table, CSV, XML file format, and it could support if multiple drivers are there. We could select driver in case of multiple drivers present in the system. So this is the example, like if you run the Python sysman command line help, so what are the options are available? It could give the all the telemetry information, what is the temperature, what is the power here, sorry, and what are the frequency clocks available, what is how's the engine utilization, memory and PC information, fabric ports. So whatever the sysman features, all features are available, what are the features available, it will show everything. So I will take some few examples and demonstrate in the slides. So for example, I want to, in a Gen 9, if I run this sysman py, what is the device list? It will show that device 0 is GPU, it is the Intel Gen 9, it is integrated GPU, and what is the UID. And in a system where I connected like multiple discrete cards, DC1, DC2, sorry, DC1, two DC1s. So then it will show what are the available devices, like 4904, device 0 and device 1, like two DC1s are connected. So that way it will show the device list information and its corresponding vendor ID and what is the name. And if you want to use the C, like what are the processor using the memory and what is the engine usage, then it will print like that. What is the device UID and what is the process ID using? What is the memory usage by that process? And what is the any engine using by that process, current process? So here it is on. I didn't run any workload, so there is no engine usage here. Okay, if I run show telemetry, it could show all the temperature sensors, like what is the current temperature overall and what is the GPU temperature, what are the power domains, and what are the frequency domains available, and what are the engine groups currently, what is the activities going on. So all those information will be shown in the JD sysman tool. when I run some workload in the background and then I run show utilization, I could see that the render engine activity is 100%. So because it's some workload in the background, we currently using the render engine, so that it is showing correctly. So that way, JDC tool could be used. And this is the collectee tool. This is in the Kubernetes where one node have connected like multiple DZ1 cards, and this is like graphical. This is an example of tool where the tool use the sysman, and we could show the graphical representation of the how the GPU power consumed here. What is the GPU frequency set for different set of DZ1 cards, and what is the memory uses for on different DZ1 cards. Like that graphical way, we could show that engine utilization. Similarly, we could add more. So this is currently in development progress. So this way we could show that. So all the public repositories are here, like the specification, loader, GPU driver, and test. So you could go through. Um, all are like open source, so anybody can go and read about it. So that's it. Any questions?
Okay, we're waiting for questions from IRC then.
Yeah.
Let's just give it a minute or two so that people can catch up.
Sure.
Okay, looks like there are no questions on IRC, so I would like to invite you to the channel in case anybody comes up with questions afterwards. And then
Sure.
thank you for your
Definitely.
talk and have a great
Thank you.
conference.
Yeah, bye.
Yep. And we're ready to go with the next talk of the day. Jaime Arteaga and Michał Mrozek are going to present Redefining the Future of Accelerator Computing with Level 0. Jaime, Michał, please take it away.
Hi everyone, my name is Jaime Arteaga. With me is Michał Mrozek. We are from Intel Corporation, and the talk of today is redefining the future of accelerator computing with level 0. What we want to show here is introduce level 0, this new programming interface that is currently available for accelerator devices. How do you use it in order to compute, in order to execute workloads in those devices, and some of the advanced features and optimization techniques that are available in this API. So what is level 0? Level 0 is a low-level driver API that is aimed at abstracting the hardware capabilities of an accelerator device. That abstraction that level 0 does is defined as being close to metal. That's why it's called level 0, meaning that it's at the lowest level of the software stack. If implemented very well, the idea is that using those interfaces, the applications, middleware libraries, frameworks, etc., can take full advantage of the potential performance of those devices, can take full advantage of the compute capabilities of those accelerators. There are different types of features available in the level 0 interfaces, such as function pointers, virtual functions, unified memory, I/O capabilities, and others that we will gonna be talking in the next slides. Level 0 is fully open sourced, so even though it was originated at Intel, there are no restrictions on being available to any vendor, to be implemented by any vendor for any type of accelerator. The links that are there are, of course, open source and can be used to see how the level 0 is being implemented so far, or what is the current status. We have a specification, we have a level 0 loader. There is a module that is device and vendor agnostic that is in charge of finding all the available implementations of level 0 in the system. We have a conformance test suite that you can use to confirm that the implementation that you are creating is compliant with the level 0 specification. And finally, we have a level 0 implementation for Intel GPUs available in the last link. Level 0 sits in the lowest level, as we said, in the user space software stack. In this case, we are seeing a GPU, an AI device, and FPGA, all of them sitting right below level 0. Level 0 could be used directly by an application, by a framework, etc. What we're showing here in the slide is how level 0 sits in the OneAPI software stack. The OneAPI is an initiative that Intel has created, or that has defined on how to approach the software stack for accelerator devices. In this case, level 0 may be called by directly by DP++ or Data Parallel C++, SQL, or by any other framework like MKL, TBB, DNN, CCL, etc., by a debugger or tools, and those will provide further abstraction to an optimized application or a middleware library or framework. So for instance, you could have an OpenMP implementation of level 0. OpenMP will provide a Pragma OMP parallel 4 that the application will use. And then OpenMP will translate that Pragma OpenMP into some level 0 calls to make full use of the target device. Level 0 is further divided into 3 types of interfaces, namely core, tools, and systems management, or SysMan. The core interfaces are aimed at providing what you need in order to compute in the in the device. You can use or you can have interfaces to discover devices, to manage memory, that is to allocate to free memory, to allocate images to free images, to submit commands and to synchronize on those commands. Tools provide interfaces to being able to debug, to instrument your program, to query for performance counters, for counters that are available in your device, for profiling purposes, etc. And finally, you have system management or SysMan that allows you to query and set an administrative, let's call it, or to manage the resources available in your system and the different settings. For instance, power, frequency, you can query for temperature, you can monitor RAS errors, etc. The way that you use level 0 is with the objects that are shown here on the right. Usually you start with a driver. When you have a driver, is that driver is implemented for a accelerator device in your system for a specific vendor. For instance, let's say that you have 3 devices in your system, 2 GPUs from one vendor and 1 FPGA from another vendor. In this case, you could have 2 drivers in your system that will be discovered by the level 0 loader. That driver will comprise a device and a context. You can create a context to start managing your resources inside the driver for a given set of devices. What are those resources that you can manage with a context? It could be memory, images, queues and lists to submit to commands to the GPU. You could have samplers for images. You could have events. You could have modules and kernels to manage a kernel or a routine that you want to execute in the kernel, in the device, etc. The device discovery pretty much works with an interface that is called zDeviceGet. After that, you get a device handle that you can use for anything that you want to do with that device. That includes, for instance, at the beginning, just querying for the properties of the device. What are the compute capabilities? What are the kernel capabilities? What type of memory is supported? What are the cache configuration? What are the peer-to-peer capabilities of that device? You can have a universal unique identifier to know what is the device that you are using, even if you have swapped it out of the system before. After you query for that device, you have a device handle that you will use throughout the program for any operation. Level 0 also defines the concept of sub-devices. If you have a device, for instance, an FPGA or a GPU, you may find very suitable to expose the device or that physical device as two logical devices or two physical devices, depending on what your device accelerator does. For instance, you could have an accelerator device that has a given number of processing units, but you want to expose those processing units as two separate logical devices. That's what you would call in level 0 as a sub-device. It will be for the application, they will be seen as two separate devices, even though they belong to the same silicon or the same chip. There are interfaces for querying those sub-devices, and the same for query the properties. They can be used for anything that a device can be used, and the very big advantage here is that the implementation of level 0 is in total freedom of defining what a sub-device is. What is its memory? What is the affinity between memory and compute? What are the compute capabilities, etc. Here there's a piece of code that shows how you can query for a device, how you can create a context, and how you can query for those device handles. Usually what you will start is with a CNET call, and that initializes the whole system. And then you continue with the following calls like C driver get, C context create, C device get, etc. Of course, for simplicity, we're not showing here error control, but of course, each of these calls are going to be returning an error that you can query to know that your call has succeeded or not. Once you have this initialized, discovered the devices, etc., you may start allocating memory. In level 0, the memory model is USM, or Unified Shared Memory. There is a single virtual address space shared between host and the devices. However, there are three types of memory defined, and there is images. So there are actually two, let's call it. There are memory that is raw, memory, linear, unformatted, etc. And there are images that are formatted allocations that you can use with a given set of parameters on your media application. In terms of raw allocations, you have three types. You have host, device, and shared allocations. Host, reside in the host, can be accessible by the device also. Device allocations reside on the devices, and they are not accessible by the host. You need to actually copy data back and forth. And you have shared allocations, which can be migrated back and forth from host to device, depending on which is accessing that data. Of course, a shared allocation provides an ease of programmability because the application doesn't need to be copying data back and forth. But implies that there's an underneath implicit migration that is happening of that data between the GPU or the FPGA or the AI and the host. How that migration happens is not defined in the level 0 specification, of course. It's up to the implementation how that happens or what kind of support that migration provides. Finally, there is also in the specification the support for malloc and new allocations. So if your host code has created an allocation for malloc and new, there's a definition in the specification of how that can be supported by the implementation. But of course, again, it's up to the implementation if it has the support to be able to manage malloc and new allocations in the same way that it does with host, divide, and share. Here we show a piece of code to create host, device, and shared allocations. As seen, is fairly simple. There's no there's no complexity here. Important part here is that for each allocation you pass an allocation descriptor, and that allocation descriptor, as you can see in the specification in the link that was provided before, each descriptor provides flags to set what you want in that allocation, to tell the driver how that allocation is going to be used. For instance, you could create a device allocation with uncached flag, which will indicate to the driver that you don't want to cache that memory. And that could be either because you have a limitation on hardware or because your specific application benefits more from having that allocation not cached. Of course, that might not be the case for other applications, but that's the idea of level 0 that provides that rich feature set of interfaces and configuration for any type of workload. The scheduling model in level 0 is based on two types of objects. There's command queues and there are command lists. A command list is a software construct. It's pretty much a vector of commands or a buffer of commands that the application creates. The application, for instance, can create a series of copies that want to perform, or a copy followed by a kernel followed by a copy that wants to execute in the accelerator device. However, that command list has no direct association with the physical device. A command queue, on the other hand, is associated directly with a input stream in your device. So if you have in your device a stream, a physical stream that accepts commands, then the command queue is going to be created against that one. It's an abstraction of that physical input stream. And what you would do is that you would submit those command lists that you have created to that command queue. Of course, one question that you may be asking is why to have two things? Why not just to have a command queue? As we are going to show afterwards, having a command list is very advantageous for optimization. A command queue can be created with with a lot of capabilities, depending on what your hardware supports. For instance, if your hardware supports a physical stream that specializes on copy operations, and another one that specializes on compute operations, on the execution of routines that the user passes, you can create a command queue with those specific flags. I want that command queue for compute, I want that command queue for copy, so that way the implementation knows what the application wants to do and can further optimize the use of that queue and the use of those lists that are going to that queue. Part of this scheduling model, we have events and fences, which are synchronization primitives to track the completion of a command. Events are fine-grained. They can tell you when a command has started, has finished, whereas a fence can tell you when a complete command list, all the commands in command list have completed. In both cases, again, it's up to the user which one is wants to use and how they want to combine them. Here's a figure that shows better what we were mentioning before about command lists and queues. In this case, we have the command list above in orange and yellow, and those comprise the commands that the user wants to submit. Those are submitted then to the command queues, which may have been created with computer copy flags, for instance, and those will be associated with the actual input streams that you have in the device. This is a piece of code that shows how this works. Pretty much you first query for the command queue groups that are available in your device. This will tell you how many input streams are available in your device, what are the capabilities that they have, if they have compute capabilities, copy capabilities. Level 0 also defines cooperative kernel capabilities, etc. How those are presented, if the implementation want to present a single group where all the input physical streams are available, or if he wants to divide them in different groups, or wants to present one input stream per group, etc. That's completely up to the implementation. The level 0 offers the ability of querying for offers the interfaces to query for those groups and just let the application to select the one that best fits the needs. Here then you query for the command queue groups, then you create a command queue. You can create it synchronous or asynchronous, of course. That means that asynchronous you submit it and then the host can do something else. And synchronous means that you submit it and you wait until it completes. So it's a blocking call. Every submission is a blocking call. And of course, then you can create a command list and on which you are going to be appending your commands. Finally, you have here the piece of code, how to create a module, how to create a kernel, and how to append it. Pretty much what the user would do is that it will have a routine written in a binary format, for instance, in an intermediate representation format, that will be passed to a kernel. And the kernel has been created against a module, where a module is a set of kernels or routines that it can be passed to the device accelerator. Then the execution of that kernel can be appended to a command list and then can be sent for execution. And finally, you can synchronize and wait for the completion of that execution.
Hello, my name is Michał Mrozek. I'm a graphic software engineer from Intel, and today I will guide you through advanced features and optimization techniques that you can do with Level 0 API. Okay, let's get going. Let's start with events and what we can do with them. Events are fine-grained synchronization primitives that allow you to properly sequence your kernels. You use them to express dependency between your command list. You can use events within command lists or between multiple command lists. There are 2 points of time that are essential for the technique that I'm describing. First is signal, and the signal happens when the event is actually transferred from non-signal to signal state, which indicates that it is completed. There is also a point of time called waiting, and for both of those, you may define what is the scope of a given action. By default, if you do not specify a scope, event just means that there is an execution barrier, and that's it. And no cache flashes are happening or invalidation. With Level 0, applications in control where the cache flashes are happening by defining those event scope flags. So if you are only synchronizing within your command list, you can and you want to synchronize only within like your subdevice, you just need to specify this scope. This allows the driver to highly optimize the event calls and make sure that the data stays in caches while you can still express your dependencies using events. If you need higher visibility, larger visibility than only your subdevice, specify larger event scope flags. But this may also mean that more and more hierarchies of caches will be flashed upon the event signaling or waiting. This technique is very useful in minimizing the amount of cache flashes and making sure it happens only when it is desired. And this is known best by the application. So utilize this scope in your application. Make sure you choose proper scope for each event you use in your application to make sure that the amount of cache flashes and invalidation is minimized. Going further, the technique that I will describe now is called command list reuse. The basic premise standing behind the command list is that they may be reused multiple times. So basically, think of a command list as a command buffer containing multiple commands. You construct a command buffer, you close it, you submit it to the hardware, and after it is actually done, you may reuse it. So you may submit it multiple times without reprogramming it from the beginning. And that saves you a lot of host overhead because you do not pay for command construction multiple times. You just pay the cost once. And that is the source of great gains and great cost overhead reduction. So when can you reuse the command list? So after closure, you cannot really modify the command lists. So whatever was programmed there needs to stay. You cannot change anything. They are not mutable. So, also, command lists may contain some state that is like one-time use, like events. When you signal an event, it's basically signaled until you reset it. So if you have a state like that that's one-time use, you would need to reset it prior to reusing this command list. Otherwise, your events would be signaled, and this may not result in proper sequencing of the kernel, which is not what you want in your application. And the last requirement that is pretty essential right now is that those command lists cannot be in use by the GPU when you reuse those with the current spec. We are working to add new flag to the specification that allows to relax this limitation. And this would allow more reuse for command lists. Like you would be able to reuse command lists even though it is running on the device at the moment. But right now, the limitation is there in the spec. So until the command list is completed, you cannot reuse it. So you need to make sure that this command list is completed prior to reusing it. Okay, let's get going with some samples. Let's start simple with a simple command list containing two copy commands, one uploading the data to device from host memory, then launching a kernel that will do the computation, then following this up with the data download to the host from the device memory. So in our command list, we would have a copy command, which will follow by barrier call that would ensure that this copy command is completed. Then we launch the kernel that works on the memory uploaded here. Then we do barrier again to make sure that the complete kernel is done. And then we transfer the data back to the host. So what we recommend here is to use host memory for host data and device memory for device data. This way, the pointers would be constant and you wouldn't need to modify them between iterations and effectively reusing the command list. And you would always be able to download the data back to the host this way without mutating this command list. The main thing when you start reusing the command list that you need to think about is how to make sure that you can do this without mutating the command list. So this command list is recorded sequence of commands, and you can submit it multiple times to the device after first programming. So this is like a simple case, but what if you want to know that this command list is down, like there are no events associated here? So for this, you can use fences. Fences are decoupled from command list. You can associate a fence when you execute a command list. You can pass a fence, and this fence will tell you whether your command list is completed or not. And you may use those fences to express to the host that the command list itself is completed, which is very useful because prior to reusing this command list, you need to make sure that it is completed because device cannot reference this command list due to spec requirements today. So those fences are not coupled with command lists. You can attach multiple. You can have multiple fences associated with the same command list. Like you can associate different fence on subsequent execute command list call. This way, you can have a fence per each command list, and you will always know which of reused command list is done or not. So use fences to express to the host that the command list is done. Okay, let's go with some more advanced scenario with events. So our copy APIs and kernels APIs can produce events, and later the APIs that are launching kernels in command list can also consume events using event wait lists. And that's what we will try to do. So we have the same scenario from the previous slide, but we are not using barriers, but rather we will use events. So the copy is signaling event 0. The kernel is waiting for event 0 and signaling event 1. And finally, the copy is waiting on event 1. Because we use events, everything is properly synchronized and all those commands execute sequentially as we wanted. But there is a problem when we want to reuse this command list because those events are signaled. So if we simply reuse this command list without resetting those events, the sequence would be broken because this kernel will start not after the copy is done, but immediately because the event 0 would be signaled. That's why you need to reset those events prior to reusing this command list. And you can do this either from the host using the event host reset, or you can do this by appending to the command list itself the reset event operation. So in this sample, at the end of the command list, we add a barrier to make sure everything before the barrier is done. And then we reset all events used in this command list. So basically, whenever we will try to reuse this command list, all those events will be in non-signal state, which is what we want. So we effectively created a reusable command list using events. Okay, let's go into even more complex scenarios where we have multiple command lists and we want to effectively reuse as many of those. So to synchronize between command lists, multiple command lists, we will use events as well. And to make sure that we can repeat those command lists, we will reset those events on the device itself. So we decoupled our workload to 3 separate common lists. One doing a copy operation, second doing compute operation, and third using another copy operation. And what is crucial here is that at the end, we have this sequence. We basically put a barrier in a common list, then we reset event within this common list used for waiting, and then only after the event is reset, we signal the event for the subsequent consumer. And why is that? I will show in a second. Why we need a sequence like that? Because it's pretty essential. And when using this technique like that, we can effectively create a pipeline using multiple iterations where each common list can be submitted multiple times. So if we go to how it looks like when we have multiple iterations, let's say we have 2 copy queues, 2 separate copy queues doing copy operations, 1 compute queue, and we reuse the same common list. So we have associated fences that will notify the host that a given command list is done. This is essential because the host needs to know that a given command list is done, because then if this command list is done, then host can actually upload the different data under this host pointer for the subsequent iteration. And this host data can be used for further iterations. The same with this fence. Whenever we say this fence is actually done, it means this command list is done, so the data was downloaded to the host, may be used on the host, so host can move it out to some other location to make sure that subsequent iteration can proceed and provide more host data. And this is also very crucial why we are doing barrier reset signal pattern. This is because we will be reusing the same command list on the same command queue. So imagine we are not doing this like that. We are not like signaling event 0 here. We are signaling event 0 before resetting event 2. It may happen that this command list would simply go because the event 2 wouldn't be reset while the event 0 would be signaled. So everything else would go further while the event was not reset. So the reused command list would actually start too soon. That's why we need this pattern where we first reset the event used for this operation, and only after that we signal the event for the consumer. This way we maintain the sequence while reusing the command lists. And with this approach, and also with this new flag that we'll be adding to the driver, where you can effectively submit the second command list while this is running, you can effectively create a pipeline where you reuse the command list while host can provide new data because it knows using the fences that a given portion of the work is actually done. And this is a very powerful technique because it covers almost zero host overhead, because all the command lists are created. So host is only submitting those, and that's a very fast operation. And we are simply reusing all those objects, all those command buffers without generating them, without paying the cost to generate them. So the host overhead is basically non-existing in this scenario. And this is pretty complex scenario where we have 3 independent engines and we have pipeline between them, and we also use events that we reset. And what is also quite interesting here is that we only need 3 events to make sure that these 3 pipelines can be synchronized. Okay. So going further, you may ask, yeah, I want to update something in my kernel, and for this I need to mutate my command list. This is a problem for me. Like, you have this scalar in your kernel, and you want to update it with a different value, and you cannot do this because the command list is immutable. So what you can do here is those tiny pieces of state and change your kernels to work in a pattern like that. And this allows you to reuse command lists even wider, because you are not limited by some simple single arguments that you need to modify. Make sure that when you do this, you also have events with proper invalidation scope to make sure that the GPU cache is flushed, because we can cache those accesses. So you need to make sure that when you update them from the hosts, the caches are also flushed to make sure you fetch the latest data. Okay, going further. If for some reasons you cannot reuse command list, you may recycle those. So in order to recycle your command list, you simply wait until it is completed, then you reset it using the command list reset, and then you reprogram it from the scratch. So why reset instead of creating new command list? This is because each command list is a set of new resources, and generating those new resources is costly. And if you reset the command list that was already submitted earlier to the GPU, you reuse those internal resources that are associated with your command list. And that's essential for performance. So if you cannot reuse command list, at least recycle those to make sure you do not allocate too many internal resources and driver needs to pin and page in them for every new command list that you create. Okay. Some techniques about unified shared memory to share. There are two main types of memory that may be very interesting for you. First is called host allocations. So think of those like allocations that are in system memory, the host memory, which host can access, and they will never migrate. So you can access this host allocation from the kernel, from the GPU, but it will always mean that the access goes over the PCI. So you don't need to transfer this memory, but the bandwidth is slower. You don't need to do explicit transfer from a host to device. You can access the host memory directly from device code itself, but the bandwidth itself is slower. But it's very useful because you skip this whole copy operation from host to device or from device to the host. Like I showed earlier, it's very useful for updating the scalar values to your kernel. The other important type of memory are device allocations. So device allocations are like an opposite of host allocation. They are allocated in device memory and they always stay in device memory. They do not migrate as well, but they are not accessible from the host. So in order for something to appear in local memory, you either need to transfer it or generate it on the device itself. And this is the decision that you need to make in your application to properly use given memory types. Like if you only access the memory frequently on the host and rarely on the device, then there may be no point in transferring this between host and device memory. Maybe just accessing the memory directly on the device using the host USM memory would be more beneficial to your application. The bandwidth may not be like highest, but in order to transfer memory from host to device, you have the same bandwidth because you are also reading the host memory from the GPU itself. So the dilemma that you have is how frequently you reuse the memory on the device side. If you reuse the memory frequently, then device allocations are the way to go because of their bandwidth. But if you touch the memory rarely, or you just write once at the end of your whole iteration, then host allocations may give you better performance. And last but not least, it's very important to understand if you can overlap your copy operations with compute. That's what I was showing with the reusable command lists, that they were like two copy operations. They would overlap on the devices that have copy engines. You can overlap compute with compute. So copy can happen while the compute operations are happening concurrently. And that basically means that if you can overlap, you have a zero cost of upload and download because this happens concurrently to your compute. And if you have a scenario like that, then always transfer the memory to device to make sure that your compute kernels do not fetch or write anything to the system memory. Okay, going further, avoid non-USM pointers because they have an overhead. Always use USM memory whenever you can. Avoid pointers like from malloc, from free, from malloc, from new. Do not pass those pointers to the memcopy calls. because driver would need to import this pointer to the GPU domain, would need to create page tables, spin this memory, and those are very expensive operations. If you can replace malloc and new calls in your application with zmem_alloc host or zmem_alloc shared, the memory would be allocated from the driver, so driver would know the memory later, and when you copy it, it will not create any additional imports. You can also replace directly the free delete calls with like a zmem_free. This way, you can seamlessly add unified shared memory to your application and benefit from fast transfers. If you cannot like avoid non-USM pointers at all, then we recommend to actually make sure to reuse command list during the transfer. So if you are doing copy operation from non-USM memory to USM memory, reuse this command list, because this command list has an import. It imported your non-USM allocation, and until this command list is deleted, you can reuse it, and this will reuse the import. And you will not pay the substantial import cost multiple times. So do not reset, do not close those command lists containing the non-USM pointers, reuse those for better performance. Okay. And last but not least, two important features that we also have in the API. First is low latency immediate command list. So instead of like building big command list and submitting it reusing, you may use low latency immediate command list. And what it means is that you basically combine a command list with a command queue, you bind them together, and when you encode anything to such command list using the APIs to encode commands to command list, this will be directly sent and immediately sent to the hardware. So this model allows you to work in a similar fashion to APIs that has queues, because the sending of command happens immediately when you dispatch a command, not after you actually call a separate API to submit a command list. So if you need low latency, use immediate command list. But in this mode, you will not be able to reuse a command list. So you always pay the overhead of command queue creation. And second important feature that is in level 0 is inter-process communication. So basically with level 0, you can take a resource allocated in device memory and you can export it from this process and import it in another process. And after the import, you will use the memory, the same memory from both processes. And this is very useful because it allows you to share the data between processes without doing any additional copies. And this mechanism is very, very important for performance for any use cases that use multiple processes and requires to share the data between those. Okay, so summarizing, we provided you what level 0 is. It's like a tip of an iceberg. It's not all. There is a lot of cool stuff there. But what we wanted to show is that level 0 is really a low-level API that allows you to take leverage of really close to metal capabilities. You can really program everything in a very, very low-level fashion and have control on all those aspects, like what happens on events, what cache flashes should be done there, what caches should be invalidated, like to what engine you execute. Everything like that is available through level 0, and application has a really high control on what is happening during the execution. All those aspects are controllable and available to the upper layers. So yeah, go to level 0, try our drivers, see if you like the level 0, give us feedback. Thank you.
Okay, thank you for your terrific talk, Jamie, anyhow. And now we have time for some questions from IRC. Bas Nieuwenhuizen asks, with multiple memory types that do not migrate, how do you handle memory pressure situations where all the device memory does not fit into the device memory? How do you figure which buffers to keep in memory?
So your command list has an associated set of resources, and those set of resources is something that combines the resources with a command list. That's one model where the driver keeps references of all the resources needed for the command list to execute. And it can actually evict everything that is not needed for the given command list to execute. There are also make resident and evict APIs, so application can take full control of what is resident and what's not. So application can directly pass USM pointers to those calls and make sure given resources are pinned and taped in, as long as it doesn't call evict operation. So application will be directly informed by a make resident call failure that the system is under memory pressure and something needs to be evicted. An application can take full control of what is evicted at this point and what should go out of the memory. So those are two main mechanisms that you can do with Level 0 API today.
Daniel Stone asks, are there any plans for independent or multi-vendor maintenance and governance of one API?
So I guess that the question goes more or less like there's going to be like a, I don't know, a consortium or something like that, I guess, right? So that's part of what we're doing right here with this activity. This one, the part of what we're doing with this activity, we're trying to evangelize, to communicate what Level 0 can do. Right now, there are not specific plans, but that's what we're hoping. The community start adopting Level 0, starts knowing more about Level 0. More, as we said, vendors of any kind, of devices of any kind can be implementing Level 0. And as we have more people, more vendors using Level 0, I guess that will be the next step.
Okay, Alex Dusher asks, is there a mechanism for governance of the API from third parties? But you've sort of already answered that, so I think it's fine.
Yeah, I guess that it will be the same, exactly.
Yeah. Okay, so no more questions from IRC at the moment, so thank you very much for your talk, and have a great rest of the conference then.
Yeah, thanks. Hope you enjoy it.
Thank
Go
you.
to our web pages, look at Level 0. Everything is up and ready for testing. So yeah, enjoy. Bye-bye.
Thanks. Hello. There are some scheduling changes tomorrow. We have a new workshop, Hostile Multi-Tenancy on Commodity GPUs. Can it be secure? Led by Demi Obenur. Have you ever wanted to play games on your computer without having to trust them? Come join us and discuss ideas for a modern secure GPU driver. This workshop is going to be scheduled for tomorrow before the originally scheduled, I believe, a security buff workshop. So check out the schedule for the current situation. And up next is the talk by Matthew Harp on X.Org security in just like 20 seconds. Okay, and we're ready to go with the next talk, and that's Matthew Harp and X.Org security. Take it away.
Hi, welcome to this talk about the X.Org security mailing list and the handling of security vulnerabilities in the X.Org project. I am Mathieu Herbe from Toulouse in France. X.Org is not my main job. but I'm the maintainer of X.Org and OpenBSD since the beginning of OpenBSD a long time ago. I started with X386 and then moved to X.Org, and I've been with X.Org Security with Alan Coopersmith since 2008. And one of the reasons of this talk today is to try to bring new people to manage this list, because I would like to be able to step down. This talk is explicitly about the handling of security issues that were reported to the X.Org security mailing list. It's not a general talk about the security of the X.Org ecosystem, the X server, the libraries, or the applications as a whole. There have been a number of talks on this subject in the past X.Org conferences, so I'm going to refer you to those talks. So within X.Org, we are aiming at a responsible vulnerability disclosure like many other open source projects. This is because vulnerabilities in widely used software like X.Org can have a huge impact on existing installation. So the process is that white hat researchers that are willing to follow this responsible disclosure process report the vulnerabilities they find privately to the X.Org security mailing list and work with the maintainers on a fix to decide on a disclosure date. This gives time for the people who manage binary packages, distributions like Ubuntu, Red Hat, OpenBSD, FreeBSD, and so on, to prepare updates ready to be installed by the package manager of each system. This is really a limitation of the full transparency that most of the open source and free software projects aim at having, but this is to mitigate the impact of 0 days vulnerabilities and exploits. So we should try to keep the embargo on the vulnerabilities as short as possible. And to help with that, some organizations, but not X.Org, have bug bounties programs to encourage researchers to report the vulnerability using a responsible disclosure project rather than publishing or selling their vulnerabilities to bad actors. On this other side, we have the full disclosure process, where the vulnerabilities are disclosed as soon as they are found by researchers and patches are not yet available, so the users get exposed to the vulnerability, which is not really good. This can happen for a number of reasons, even if an organization has a responsible disclosure policy in place. For example, Black Hat researchers may choose to sell their vulnerabilities rather than cooperate with the organization. Or there can also be mistakes from developers who honestly didn't see the security implication of a bug fix, and this implication is discovered only after the fact. On the X.Org security mailing list, we have a number of actors involved which need interaction. The maintainers of the various subsystems on the left here, and the people representing the various distribution and systems that ship X.Org server and libraries on the right side of the slide. In total, there is about 35 people on the X.Org security mailing list representing all those people. In these slides, I'm presenting external actors and the associated vocabulary for the handling of security vulnerability. MITRE is a public US company which is playing an important role because they are assigning identifier to the vulnerabilities, common vulnerability exposure identifiers, which are numbers that uniquely represent vulnerabilities and allows us to refer them in a non-ambiguous manner. MITRE is also delegating the attribution of those numbers to CVE numbering authorities, or CNA. Red Hat, for example, is a CNA, and they play the role of default backup CNA for all open source projects that don't have an existing CNA on their own. The OSS security mailing list is a mailing list where many open source software exchange information about their vulnerabilities. The distro mailing list, on the other hand, is a closed mailing list where only recognized Linux distributions can synchronize themselves and cooperate on the disclosure of on new vulnerabilities. And there are a number of computer emergency response teams, CERTs, like the US CERTs and other CERTs. For example, in France, we have 2 different CERTs, one for the public domain and another for private companies. Often for open source software, or small open source software organization, interacting with the CERTs is a bit difficult because we don't have the same time frames and way to see things. In order to give you an idea on how things happen when a vulnerability is reported, I'm going to play a small fake example of a vulnerability. Let's say that on March 6, 2019, someone called Jolybug sends a report to the X.Org mailing list about a vulnerability in libxfoo. Then some dev, a member of the X.Org list, confirms the existence of the problem, analyzes that it was actually introduced by a change in a previous version of the library, and so they answer to Jolybug that they got their email and ask them if they already have allocated a CVE ID and if a disclosure date has already been set for the vulnerability. Jolybug answered that no, and this is actually open both for the date and that there is no CVE ID. So the things go on. Some dev ask Red Hat as a CNA for a CVE ID. Someone from Red Hat actually allocates a CVE ID. And then, since libxfoo is widely used, we also decide to tell the distro mailing list about the vulnerability, and we set up an initial release date for the 22 of March, 14 days later. Someone from the distro mailing list answers that this is a bad idea because it's a Friday. Vulnerabilities are better released in the middle of the week, for example, on Tuesday. So we set it up to the 19th instead. And also, in this process, someone discovered that the proposed patch was not covering all the cases where the vulnerability is present, and so we need a wider patch to cover all the cases. Once a full patch is ready, it's sent again to the security list, to the original reporter, and to the distros list. At the same time, the advisory is prepared, containing all the relevant information, and a new release of libxfoo is also prepared to be able to fix the issue. And on the disclosure date, March 19, the new version of libxfoo is released, the advisory is sent to the mailing list, the wiki page is updated, and on their side, Jollybrand sends their advisory to a number of mailing lists and social networks. And so now the bug is public, and the distros have been updated their binary packages, and the package managers of the users are updating the package. Might unveils the CVE ID, and the various certs and news sites like Linux Weekly News or Foronix publish their own news on the bug. That's it. Now let's talk a quick bit about classification of the vulnerabilities that have been reported since 2008. In the early days, we had mostly quite critical bugs, buffer overflow, argument sanitizing bugs, and so on, that almost always gave direct root access, also because the X server was running with full root privileges at that time. Nowadays, more bugs are more subtle, mostly protocol handling issues, decoding issues, that lead to various uninitialized memory read or extra memory read, and in some cases a few bytes of memory writes. We also had a number of file format decoding issues, mostly fonts, but since nowadays FreeType is handling the fonts for most of the time, and FreeType is not part of X.Org security, it's out of our scope nowadays. There are a number of mitigations, like the fact that we have less privileges in the X servers and clients nowadays, and that XCB, by automating the decoding and encoding of the protocol, helps quite a bit with security issues, but the server side has not been done yet, and there may also be some issues still in the XCB code itself. So what's the current state and a conclusion on this talk? All the code base is quite old, often more than 30 years old. And so this means that the knowledge of this code is slowly fading away, making us less reactive, because we need to spend time studying the code and trying to understand the state of mind of the original authors. We really need the new people to help with this process. We may need to fix the way that we get CV IDs. Either we can stay with Red Hat or become our own CNA. Another issue that I see is how to integrate the process with GitLab. Currently, there are private issues in GitLab, but we don't really know who has access to the private issues in GitLab and how to actually transition the handling from the X.Org security mailing list to the people who have access to the private issue on GitLab, making sure that distro representatives and the original reporter can have access to the private issue in question. And more generally, I think that to get more people involved, we should start to get more involvement from the vendors that are actually on the X.Org mailing list, hoping that they can provide more patch reviews and also help with the improvement of the existing code before the vulnerabilities are reported. For example, it would be really great if someone could help with moving the X server protocol handling to XCB. And there is a BOF session tomorrow afternoon to discuss those issues for those who are interested. It's 16:30 for the end of the talk. If you get the PDF of the slides, there are a number of links to various resources that I mentioned during the talk. And if you have questions, hopefully we have some time right now, or we can discuss this more thoroughly tomorrow during the Bird of a Feather session. Thank you for your attention.
Okay, thank you very much for your great talk, Mathieu. And now it's time for some questions from IRC. Although it looks like there are no questions at the moment, so we'll wait a bit. Also, one minor correction. The BOF tomorrow is moved an hour forward versus what was on the slides. So please check out the schedule for the current up-to-date time.
Okay. Yeah, my goal with proposing a workshop or a Bird of a Feather session for tomorrow was to be able to discuss the issues that I mentioned in the talk more widely. If people are interested, we are really going to welcome new people to try to handle the remaining issues in X, because X should be deprecated at some point, but there are still probably a few years before it actually completely disappears from the Linux or BSD desktops.
All right, it looks like there will be no questions for now, so please stay around on IRC in case some do appear after all. And thank you for your talk, and have a great rest of the conference.
Welcome.
Thank you very much. Okay, and with that, we are going to end the day. we've just reached the last talk, and the board meeting itself is not streamed or recorded. So with that, I'll leave you with some background music for the next few minutes, and, well, see you tomorrow.